In this video, we are going to build a simple Git from scratch using Python. This Git will support operations like init, add, commit, log, status, checkout, and branch. This tutorial's goal is to give you an intuition of what happens behind the scenes when you use Git commands. I think the best way to accomplish this goal is to rebuild Git from scratch. Get subscribed and let's dive in. The first thing that we're going to do is create a folder where we can store our files. So I'm just going to create a new directory called git clone. After that, I'm going to move into this directory so that I'm no longer in desktop. I'm in this particular folder I created. And then I'm going to open it in my favorite IDE, Visual Studio Code. If you want, you can use some other IDE, but I'm fine with Visual Studio Code. I'm also going to zoom in a little bit so that you can see. After that, I'm going to create a new file called main.py. This file is where all of our logic for git clone is going to reside. I'm not going to be splitting into multiple files, so it's going to be about 1,000 lines of code in just one single file. That's probably not a good structure, so you should just split it in multiple files, but I just like it this way for a simple project. The first thing that I want to do in this main.py is create a function called main. And then I'm just going to pass like a placeholder over here so that it doesn't give any syntax error. And then before I forget, I'm going to call this main function. Cool. Now I'm also going to minimize this Explorer tab so that we can have more space to ourselves. Then I'm going to open the integrated terminal. So to open it, you can just go to View, Terminal, and then it will open up. For me, I've created a keyboard binding such that when I do Command J, it opens up and closes for me. So I'm just going to use that from now on. Now to execute this main.py file, as you would know, we have to do Python 3 main.py if you're on a Mac. If you're using something else, maybe you can try Python main.py and it should still work. So either of these things should work. Just to ensure we are on the same page, what I'm going to do is type in Python version, not Python 3 version, because I'll continuously be using Python 3. If I do Python version, it is going to be 3.12.7 because that's the version associated with this Python. But if I do Python 3, it's 3.9.6 and I'll be using the 3.9.6 version. So yeah, after that, the very first thing I want to do is take some input from the CLI, because Git is essentially a CLI tool, right? So we want to ensure that we can take some input arguments from the user. So the user can type in something like Python 3 main.py, let's say init. So init is going to be the first method, or let's say the first input argument that we're going to support in this git clone. So I want to ensure this can happen. And if I do this, it does look at this init and call the specific init method. All right. Now to take an input, we can use something known as argparse. So at the top, you need to import argparse. This is built into Python. So we can just use it like that without doing any pip install or anything. After that, we can do argparse.argument parser because the user can pass in a CLI command, right? We want to extract those arguments from the CLI command. And this is how we are going to initialize it. I'm going to call this parser. So we have an instance of this. Now, if you want, you can pass in multiple things like prog, usage, description. I'm going to pass in description so that, it looks cool that we have, let's say, pygit or whatever you want to call it. I'm sure you can come up with a cooler description, a simple git clone. After that, we're going to add something known as subparsers. Subparser means it allows us to create subcommands within the CLI application. So I'm going to create subparsers like this, which is equal to argparse.add subparse or add subparser, I think that's how the function is called. And then I'm going to specify a destination. So the destination for us is going to be command. That means if the user types in something like Python 3 main.py init is going to be stored in this command variable, which will be accessible through an args property we'll see later on. And then in the help, we're going to add in available commands. All of this will make sense once we, have certain amount of code so that you can understand why I'm writing all of these things. After that, what we're going to do is add the support for init command. So now we're going to create an init parser. which is equal to subparsers.add parser. Now you might be wondering, what is the difference between this add subparsers and add parser? There is a difference. This add parser method is used to create and add individual subparser to a collection of subparsers. So when you call add parser, you're defining a specific subcommand that can be invoked from the command line. So that's why we're going to have init command over here. See here, I can type in init, and in the help part, we can just write that this allows us to initialize a new repository. So that's what add parser allows us to do. We are defining a specific subcommand that can be invoked from the command line. And now you can use this init parser to add specific arguments to this parser. So to give you an example, git init is probably not the right example. Let's say we had python 3 main.py add. Okay, so this acts like git add. Now, just doing git add isn't enough, right? We need to add the files that we want to add to git. For example, main.py. So after add, we have another argument that is in relation to this add. So that's why a parser is created here. Using this parser, I can call something like this, init parser.add argument. And this will allow me to add any more arguments after this init. For example, git init, and then I have, let's say, help. So an argument of help can be added here. That's what the parser allows us to do. A subparser, on the other hand, is essentially an argument parser instance that is associated with a specific subcommand. And in our case, that is command. This subparser allows us to define a separate set of arguments and options that are only relevant when that particular subcommand is used. So you can think of add subparsers as kind of like a container for each of the subparsers. And then add parser is called on that specific container to define each individual subparser. If that doesn't make sense, don't worry, we'll see it in action. So with just this much, we've added support for init command. Now I can just do parser dot parse args. That allows us to, take in the args that the user has specified and get it in a format usable to us. So what I'm going to do is go ahead and print this args. After that, I'm going to open up the terminal and then just type in python 3 main.py init. And this gives us an error, attribute module argparse has no attribute add subparsers. And that's correct, because add subparsers should not be called on argparse, it should be called on this parser. So parser.add subparsers. And now if I do python 3 main.py init, you can see we get a namespace object with command equal to init. That's exactly what we have done. We have said that we have an argument parser with this description, then created a subparser, and then used this subparser to create multiple commands. So init is one of the commands that's supported, add will also be supported, commit, status, log, checkout, branch, all of those commands will come under this specific subparse, which is a command. And each of them is going to be stored in this destination of command. That's why if you see namespace command is equal to init gets stored. If I do, let's say main.py add, it says invalid choice add, because we don't support add as of now. And then it also gives us a usage that, hey, if you want to use it, you can do main.py /h if needed, main.py -h init. It gives us the description of this. So we get get a simple git clone, then the arguments that are available, which is init. And what it does is initialize a new repository. So having understood how to take in input arguments, we can move forward. The next thing we want to do is that, let's say the user does not specify any of the command. In that case, we want to print out the help message. The reason we want to print out the help message is because, let's say the user types in main.py like this. They probably don't know what to do. This is why they've done this. For example, if the user just types in git, we get a help message, right? That's exactly what we want to do. That's why what we're going to do is if not args.command, because we saw that all of our data essentially gets stored in the command, right? So if not args.command, That means it is empty or it is null. In that case, we're going to use this parser and print out the help message. Print help does that. And then we're going to return so that we don't execute any further because we have other stuff to do now. Let's save it and again run it. Well, now we don't see anything, but if I do main.py, we get the help message. That's great. Just a simple step towards usability. After this, what we're going to do is support the init method. The next thing we're going to do is if the user does pass in init as the command, then what do we want to do? Well, we want to initialize the repository and we're going to create specific commands for that. So first of all, I'm just going to create a try and except block because there is a probability that something wrong happens over here. So it's in a try and then exception as E. And then what I'm going to do is print out that, hey, we have an error and this is the error message. And after that, I'm also going to do system.exit1. Or if you want, you can just leave it over here, but I would just like to have some closure. System.exit1 should be fine. And then we'll also add import system at the top. Yep, that sounds good. Now what do I want to do? Well, I want to check if the arg.command was init. If it was init, then we want to initialize the repository because as we know, we're going to add support for multiple things. If we do add parser, let's say add, right? That means we're also supporting the add command. If I do add, you'll notice it successfully passes. And the reality is that the data will be stored in args.command. So if I just print out args.command, then do python3 main.py add, it says add. If I do init, it prints out init because it realizes what the command is. Everything will be stored in this command destination. That's why what we are going to do is if args.command is equal to init, then we are going to initialize a repository. Now, how do you initialize a repository? Well, we'll have to create stuff for that. But before we get into initializing a repository, we first need to understand how real Git does it. And for that, I have created a test folder called git test. Here, I'm just going to ls so that you see that we have a hello.txt file and hi.txt file. There's nothing much in these two files. It's just like hello world and then the other one is, hey, this is a test file. So nothing much, and there's no git folder here as well. So we are going to initialize the repository as you can see. So once I do git init, what do we get? We get initialized empty git repository in this particular path. And you can see that it creates a new folder called .git. If I do ls-a again, we have this .git folder along with the rest of our files. Now, what is this .git folder? That's Git's way of storing stuff. One misconception that I've seen many people have is that they confuse Git and GitHub. Remember, Git is a very local tool if you think about it. GitHub is like a repository to store it online, but Git can be used as a standalone tool for your own machine. Let's say you have a project which you don't want to upload online in any form. You just keep it to yourself, but you still want the version control management system. You want the version control management system because you are sure that your AI or whatever tool you use is going to disrupt your code. You want to create one snapshot and save it in your local system. That's when you can use Git. Now, if you upload it online and use it to collaborate with people, that's another way you can use Git and GitHub or GitLab, whatever you use. But Git is a very standalone tool. It can be used as a standalone tool, remember that. And I think GitHub also uses this .git folder to understand the content. For example, if you open a pull request on GitHub, it creates something like a diff, right? You have all of the changes that can be seen, some in red, some in green. Where's all of that data coming from? How does GitHub know about it? GitHub knows about it from .git mainly. This is the ultimate source of truth. Everything is going to be in this .git folder. It is kind of like the database of Git. So let's go into this .git folder and understand this. So I'm going to do ls-a here as well. And we see we have multiple files. We have head, we have config, We have description, hooks, info, objects, refs. Now, we are not creating a full-fledged Git system. So obviously we are not going to implement all of these folders that get initialized. What we are going to focus on is head. We are going to have objects. We are going to have refs. I don't want to overwhelm you with all of the information at once, but briefly I'll just tell you that head is used to store what branch you're currently on. Objects is used to store all of your objects. There are mainly 4 types of objects that we are going to discuss later on. But yeah, it stores all of the objects that are present in your Git project. So it can be something as simple as a file. It is stored as an object. So let's say I want to add this main.py to the version control system. I do git add main.py, right? So this main.py file is stored in this objects folder. As of now, if you see, the objects folder is going to be empty. So I'm just going to do ls objects, and there we have info and pack. But if I do ls of info or pack, you'll notice both of them are empty. They're just folders created where data can be stored. Now, obviously we are not going to have info or pack. We're directly going to store our data in objects. Anyways, I'm getting ahead of myself. We have objects then, and then refs is going to contain references to the branches and all of that stuff. This is a bit complex to understand, so I'll not overwhelm you. But yeah, that's the core thing. We're going to have these folders when we call init. And essentially what happens when you call init is that a repository is initialized, and when it says repository is initialized, a .git folder is created. So let's go ahead and create a class called repository. This class repository is going to contain all of the essential functions related to the management of repository class in Git. So we're going to have def __ init. What this does is like initialize the repository at a given path. So we are going to take in a path variable, and by default it is going to be dot. Dot means the current file or current folder we are in. After that, we're going to create a path. So we're going to have self.path, which is equal to path. And path is again another thing that comes from the Python language itself. We're going to do from pathlib import path. Here we're going to specify the path. It accepts the path, well, obviously, and then we're going to call resolve on it. What resolve does is it gives us a path, making the path absolute, resolving all symlinks on the way, and also normalizing it. Essentially, when we are passing in, let's say, git init, we are passing in the current folder we are in, right? We want to initialize this particular repository. So that's why dot is used, but the actual path that we want to store should not be relative. So again, when we call git init, we are saying relative to this folder we are in the git clone folder. So relative to this folder, we are saying that in this folder, we are adding init, but the actual path should not be this, right? It should be an absolute path that's created. For example, if I get out of here and do git init, it says initialize existing Git repository in this particular path. This is the path we need, the absolute path, not the one that we do git init full stop, right? That's why we have this path done, and resolve just creates an absolute path out of it. After that, we're going to create multiple things. So the very first thing is going to be the git directory. Then we're going to do self.path /.git. What this means, or let's just call it pygit, by the way. If you call it .git, and let's say you call python3 main.py init in this specific folder, it will mess up your existing Git repositories if you have one. So let's say you want to store your current project, the Git clone we are working on let's say GitHub. So you'll do git init for that, right? And that will create a .git folder. But if you also create a .git folder here, and then call your app specific python3 main.py init, it will also create a .git folder. And then there'll be many issues. So obviously you don't want that. And that's why we're going to call this .pygit. After that, we're going to initialize multiple folders. We saw, for example, we have .git/objects, right? We're going to create that. So we're going to have self.objects objects directory is equal to self.get directory / objects. By the way, / just does the job of concatenating. So if the absolute path was something like this, it will just add objects after this. Now, similarly, we are going to do it for refs. So we are going to have self.ref directory is equal to self.get directly /refs. After that, we are going to have a head file. So let's also create a head file. And then we have self.head file is equal to self.get directory /head. There's also another file that's used, which is the index file, which is related to the staging area if you know about how Git works, but I'm going to explain that. So as of now, what I'm going to do is just create it. There's also another folder in refs, but I'll just get to it later on. As of now, we're just going to have .get /index, which is kind of like the staging area. Not kind of like, it is the staging area. So we have self.index file, which is equal to self.get directory /index. That's great. So with this, we have initialized all of the variables, but these are just variables. We want to create folders out of them, like actual folders. And that's why we are also going to create an init method. And this init method is going to be called when the user calls in the init command. So this is going to create and initialize a new Git repository. And the return type of this function is going to be Boolean. We'll understand that why in just a minute, but first let me just create and initialize a new Git repository. So the very first thing I'm going to do is take, let's say, self.get directory. I'm going to create that before anything else. So let's call .make directory. Then similarly, we are going to do it for objects. So we have self.objects directory.make directory. Then we have ref directory, self.ref directory.make directory. After that, head file. So there we go. And actually, head file is not really a directory, so we don't have to do that. We'll do something else. The same goes for index file. So let me just add in a comment, create directories here. After that, we're going to have create initial head pointing to a branch. So a head file is created which points to an initial branch. So like, what is the default branch? In our case, if we go to .git and check out get head, you'll see that by default, it points to main. That's the thing. And it does refs heads main. As I said, references is a bit tricky to understand. It's not difficult, but it can be a bit complex. So I'll just get to it later on, but essentially it's like a symbolic pointer to this refs folder. It's saying that the default branch is what's stored in refs heads main. And in refs, we do have heads, another folder that we'll have to create. So if you don't mind, I'll just create it right now so that I don't forget it. So I'll just have self.heads directory is equal to self.ref directory /heads. And within this heads folder, we're going to have branch names. For example, main, master, or any other branch you create. So that's why here we are going to have self.heads directory.make directory. And now we create initial head pointing to a branch. In our case, master is going to be the initial head. In the early days of Git, or probably even 3 years ago, I think, master used to be the default branch. Now main is the default branch. So to make our Git a bit different, we are just going to do self.head file.write text. It will start writing text to it, and the text we want is refs heads master. If you want, you can name your thing any other thing. Also, I'm going to put \n so that I leave a line. After this, I'm also creating an empty index. As of now, you'll notice there's no index file created here. I'm going to create one. The thing with index is it stores the file in a JSON format where it creates a mapping between the file name and the hash related to it. Again, don't worry about it. We'll come back to it when we actually work with the staging area, which is the very next command, get add. But I just want to initialize it so that, we don't jump back and forth with it. So as of now, I'm just going to do self.indexFile.write text, and the text is going to be JSON.dumps. Then we are going to pass in an empty dictionary. And then I'm also going to specify the indent to be 2. That's it. Now let's import JSON at the top, and that's it. Also, you have noticed that the return type here is a Boolean. So if everything goes well, what we're going to do is print out this initialized empty git repository in, and then we need to specify the path it was initialized in. So we're going to have self.get directory, the absolute path that's stored, right? So this is the self.get directory, the absolute path. Okay, that sounds good. After that, I'm going to return true here. But when do we return false? The Boolean here indicates that the init method was successful or it was not successful. So in our case, it will return false if the git directory already exists. If the git directory already exists, that means it has already been initialized. And if it has already been initialized, we want to return false. So here I'm just going to have if self.getDirectory.exists, that means it's already pre-existing, we return false. And if it's not existing, then we create it and return true. Great. Now all I need to do is down here, if args.command is equal to init, I want to create a repository. So I'm going to do repository is equal to repository like this, and then I can call the init method on it. And after that, I'm just going to call repo.init. But we know that repo.init gives us false, and it only gives us false when the git directory exists. So that means if the repo init is false, git directory exists, that means we can just say print repository already exists. Or if you want the same wording as git init, you can just do reinitialized existing git repository. But I prefer this one because I'm sure behind the scenes they're doing something else. There's a lot more they do. In our case, we're just saying repository already exists. That's good. And we've also called the repo.init, so that means everything should be initialized, just in case we get a true response. So in case of false, it gives us this print, and also let's return out of here. So if it is true, then it's going to initialize everything and give us initialized empty git repository. If it's not true, that means it's false. It will give us repository already exists and return out of this entire program. Great. Now let's save it, open up the terminal and try some stuff. So I'm going to open up my File Explorer tab. We're going to see something new hopefully now. Then I'm going to do python3 main.py init, and it says initialized empty git repository in this particular path. Then we open up our .pygit and we see objects, refs, head and index. Within objects, there's nothing. Within refs, we have one folder, heads. Generally in refs, you also have another folder called tags that's related to annotated tags. If you know about them, good. If you don't, I can quickly show it to you. So if you go to git, you'll notice that there's a source code of Git uploaded online. It's open source. And if you go to this 990 tags, you'll notice this is what tags are. Tags are kind of like commits, but with additional messages. So generally they're used if you have a release version 2.51.0. So it's created as an annotated tag. So these tags are also stored in this refs folder, but I'm not going to go into it. If you need a second video that captures all of this, let me know. I'll be happy to create it if you're interested. But as of now, let's focus on the fundamentals. So we have heads, but we won't bother with it as of now. We'll get to it later on. Then we have head, which just says refs, heads, master. Then we have index, which is empty, but we're going to populate it in the next command. We're going to add support for git add. Right now init is done. So git add, and the structure of git add is that you do git add and then you pass in the path. Now this path can be a file name and it can be a folder. So we need to understand ourselves that has the user passed in a path, or have they passed in a folder, or have they passed a file name that does not exist in this folder. So that's like the three cases we need to think about. And once the user does it, we need to add it to the index. I'll show you a simple working in .git. Okay. So as of now, there's no index file, right? Now I'm going to go back and I'm just going to do git add hello.txt. Now look, if I go to .git again, do ls, we have a new index file created. And if I cat index, that means I'll be able to see it. Now we get a bunch of things that don't really make sense, but we have a hello.txt in between. Essentially, there's some sort of mapping going on here between the file name, the file that you just added hello.txt, and some form of linking it with the object. So if I go to the objects folder now, ls it, I get 27 written out over here. If I go into 27, ls it, I get some weird number written out over here. And now if I just do cat of this thing, I get some weird thing again written out. Now all of these weird things are present because all of it is in a bytes format. In Git, everything is stored as bytes. Not everything is stored as bytes, but all the objects are stored as bytes. They're compressed and stored as bytes. Why are they stored as bytes? And by the way, just to prove to you that this is not a folder, I just tried to do cd with this thing and it says not a directory. So it is a file. Now, why are they storing it as bytes? Because the reason for that is your file can have images, right? How do you represent images plus text plus audio plus video, maybe all of that in one format? Bytes. Bytes is the best way to go about solving this discrepancy. Everything can be transformed into bytes. That's why everything is stored as this weird characters, bytes. That's what git add does. So to explain this git to you, I'm going to separate out everything in three formats or three working areas. So there are three areas you can work in Git. You might have heard of it. One of them is called the working directory. So let's call this working directory. Then the next area is called as staging area. And the third one is known as local repository. Now, if you want, you can definitely add more to this, but these are essentially the main three. When I say you can add more to it, there's also like support for stash, right? So there can be another area for stash. Even refs can be considered as another area. And you can also consider remote repository as the fifth one. But these are essentially the three pillars I would like to focus on. So the working directory is like the directory you're working in. You have all of your files here listed out, like hello.txt. Then you have hi.txt. Then let's say you also have a main.py. Then you also have, let's say, image.jpg. All of these things are going to come under working directory. So working directory is nothing more than the files on your disk, right? Anything that's present in the directory you're working in or you're on your system, all of it is going to be present in what's known as the working directory or the working tree. These files are probably not yet tracked by Git, or they may be tracked. I'll get to it in just a minute. There's like a case where they might be present, but essentially they can be considered as files that might or might not be tracked by Git. Now, the second area is the staging area. Now let's say you want to move this hello.txt from the working directory to the staging area. What do you do then? Well, that's when you use the command of git add. And if you do git add hello.txt, what happens is that you copy this hello.txt from working directory to the staging area. And what the staging area does is that it will first of all store your object in git/objects. So the way it stores it is that it takes your entire content. Let's say hello.txt was 2000 lines of code or 2000 lines. It will take that 2000 lines, all of it. It is going to compress it. It will compress it in bytes format so that it doesn't really lose its data, but the size minimizes down. This is known as lossless compression. So it does that lossless compression so that none of your data just, vanishes, but still the size is relatively small. And then it stores it in Git objects. Okay. After that, it maintains what's known as an index. This index is like a mapping between the file path. Let me just call it FP. This file path will be mapped to the hash that's stored in Git objects. So there's a subtle difference here. When I said that you do git add, what you're doing is copying the file content, let's say the 2000 lines. You take that and you compress it. So that's stored in a file, right? And it contains all of those bytes. This is with the lossless compression. Okay. But the file also needs to be given a name, right? What is this file's name? This file's name, if you notice, was a bit weird again. Let me go back. I'll clear everything off. ls, then we had 27 written over here. And then we went into this 27. Then we ls again and we see this hash over here. So we need to hash this file content, which will give us this hash. And the hash exactly is 27 followed by this thing. What Git does is that it takes the first two characters, it creates it as a folder, and then the file is stored within this. The reason it does that is because think about it. If you have 1,000,000 files in your repository or even 1,000 files, if you just store everything in this objects like a plain file, it will get so lengthy. You'll have your entire file or your entire folder here, and each of the object is plainly listed out over here. If you want to find out one file, you have to traverse all of those 1,000 files. That's not an elegant solution. That's kind of like a linear search, right? And we all know that's O of n. And if your n is a lot, like, all of the big tech have so many files, even your personal project might have a lot of files. You can't store all of it linearly. So what they do is hash your content. So it gives like 20 characters or something. Then you take the first two characters of those 20 characters. Let's say A, B, C, D was outputted. Let me just add all of these things. Then it will just take those A, B. It will create a folder, and then rest of them will be added as the file name. Okay. So what this will do is that instead of storing it like this, what you do is you have a file like this. You have a folder called AB within which you have C, D, E, F, G, H, followed by more folder names here. And if another hash is present, which is AB, let's say D, E, G, that will be stored over here as well as another file. This is very cool because first of all, we don't miss out on the complete hash. If you want the complete hash, it is called ABDEG or ABCDEFGH. And second thing is that it's no longer O of n. Everything is bucketed in a certain logical format. And that reduces the time it takes for us to find out a particular file. So this is where time complexity comes in. Pretty cool, right? And that's a very elegant solution as well. So that's what we are going to do. We're going to take the content, we're going to hash it. We're going to take the content, we're going to compress it. After compressing it, we are going to store it in Git objects. And after hashing it, we are going to name that file like that. And then the hashed format is going to be stored over here because we need to identify this file name with the hash that's present. If you just have the hash, it will get difficult to find out what exactly is being tracked, what exactly is not being tracked. So you just have this index file that keeps track of, file names to hashes. If that doesn't make a lot of sense, don't worry. When we write the code and I explain it again, it will get much, much clearer. But as of now, let's add support for the add command, and then we'll go ahead and create stuff for this repository. So let's go ahead and add support for the add command. So the first thing we're going to do is create an add parser, obviously, and the help message is obviously going to be add files and directories. We're going to add support for files and directories both, as I mentioned, to the staging area. Great. Now, just having add is not enough. Also, I'll just add a command here, add command. Now, just having add is not enough because, as I mentioned, you can have git add followed by, let's say, a full stop. That means you want to add the entire directory. Or if you want to add, let's say, .pygit/objects, right? That's a folder. Or if you want to add a particular file, all of that needs to be supported. So you need another argument that takes in the paths. And that's why we're going to create add parser dot add argument. This allows us to specify an argument after add. So if you notice, we had add parser over here, but here I have add argument. So within this parser, we add support for the argument, and then we can just say paths here. Then the nargs can be mentioned. Narg stands for the number of arguments. If you pass in plus, that means the user can pass in one or more arguments and it will be collected in a list format. And that's what we are going to pass in. You can also have a question mark here, which stands for 0 or 1 argument. So that means it's an optional argument. Or you can have asterisk. That means it can be 0 or more arguments which are collected in a list. But in our case, there needs to be at least 1 argument present. And then the user can pass in more. For example, in real Git, you can just do git add main.py head, or let's say file.txt, all of them together. And then main.py head and file.txt will be collected as a list, and then we can iterate through that list whenever we want. So nargs is plus, and then the help message is going to be files and directories to add. So you need to specify the path to the files and directories to add. After that, we can add support for the add command down here. So we're going to have elif args.command is equal to add. In that case, what we want to do is, again, we need to check if the repo.git directory already exists. If it does not exist, that means it's not a Git repository. Otherwise, we can just go ahead and loop through every path and add support for it, meaning add it to the staging part. So first things first, what we'll have to do is take this repo out of here. The reason we have to do that is because a repository will be created for each and every operation now. Init will have it, add will have it, log will have it, status will have it. So there's no point of gatekeeping it within like an if condition, right? After that, we are just going to check if not repo.git directory.exists. If the git directory does not exist, then we are just going to do print not a git repository. So you need to first initialize it. And then we can just return because it's kind of like an error message. But if the repo.git directory exists, by the way, repo.git directory means .git within this repository's path is present, and the path is always full stop. Because when you do git init, you're initializing in this specific folder. That's the only support we have. If you want to support git init and then pass in a path which will initialize the repository in some other path, go ahead, add the support for that, but let's keep it simple, right? After that, what we're going to do is for every path in the args.paths that we receive, so args.paths will have it. And if you don't believe me, it's a good thing you don't. We can just go ahead and print arg.paths, args.paths actually. And then I'll just do main.py add main.py. And as you can see, the path gives us main.py, which is present in a list. If I pass in main.py and let's say .pygit, we have both After that, we can also add readme.md even though it does not exist, and it will list it out. So all it's doing is listing out all the paths. As you can see, readme is not present. It doesn't do any of those error checkings. Why would it care? We have to handle that by ourselves. So we'll have to check the validity of the files if they are even present in the first place. So here I can simply call repo.addPath, and now I need to create a function called addPath within the repository class to add support for the path. So there are multiple things we have to do. So the very first step for us is figuring out if the file or directory even exists. If the file or directory does not exist, we need to raise an error or an exception. If the file or the folder is present, we need to figure out, was it a file or was it a folder? If it's a file, we need to add the file directly to the index. So we need to store it to the object and etc. And if it's a directory, we need to list out all the files that are present in that directory recursively, because there's a possibility that a folder has a folder which has a folder within which there are files. So we need to get all of the files and list it out. So let's go ahead and in the repository, create a new function and let's call this add. We'll have a self, then we also get a path which is of the form of string. And this will probably not return anything. And it should not be called add, let's call it add path. After that, we need to get access to the entire path, right? The path the user specifies, for example, main.py, add main.py. This is just a file name. We need to get the entire path to figure out if the file exists or not. So to get the full path, what we do is self.path, which is at the top. Remember this path? We take this path, which is the absolute path of where the folder is, followed by the concatenation with the path the user mentions over here. That's the entire path. Okay. After that, we have if not full path dot exists. So if that does not exist, we just raise a file not found error. And then we can say path, and then we specify the path here, not found. Or if you want, you can just give in a full path so that the user has more clue of, well, what was the path. But in our case, path should just be fine. After that, we need to check if the full path is a file or not, or it's a directory. What is it? And for that, path is very nice. I mean, path as in this path, okay? This path is very nice because it gives us access to a method called isFile. So it tells us whether this path is a regular file and it's a Boolean value. And if it is, then we want to call self.addFile, then we pass in a path. We'll have to create this function, which we'll do. Otherwise, we'll check if this full path is a directory. Again, this is a Boolean returning function present in path module, this path again. And if it is, then we'll just add self.addDirectory, because both of them are quite different in a way. They're different because here we need to add one file, here we need to add a list of files potentially, because a directory can have a list of files. Otherwise, if they're none of them, I don't know what they are. So I'll just raise a value error saying path is neither a file nor a folder or a directory, whatever you want to call it. Let's maintain consistency, nor a directory. Okay, great. Now we need to create two functions, add file and add directory. Let's just create it on top of this. So we have def add file. What it does is have a self, it takes in a path which is string. And then what this is going to do is take the file, put it in the staging area, but before putting it in staging area, it has to read the file's content. So let me just label out the steps, all right, one by one. So the first thing is read the file content. After that, we need to create something known as a blob object from the content. This blob stands for binary large object. You know, I mentioned that if we want to put this hello.txt from here into this, we have to store it in .get/objects, which acts like a database. So it is a database that contains like the information about all the objects. And I think it's the time for revealing that there are 4 types of objects. So let's classify them here. There are 4 types. We are only going to probably create 3 of them. The first one is blob. That stands for binary large objects. So any file you have or any folder you have, like all of those things will come under this blob. Then we have commit. So commit is also treated like an object. So each commit will be created as an object. We'll understand that in commit when we do git commit. Then we have trees. I don't think we need this for add as well. Add is just about adding to the staging area. And for that we need blob because we need to store it in git objects. But trees is required when you do commit. So it will make sense of the entire structure. So that's like another object. And the fourth one is tag. These are related to annotated tags or whatever, but we're not going to focus on this one in this tutorial. We're only going to focus on these 3. And they do set up the fundamental git operations. So I'm just going to make sure that this thing is not present anymore. You only focus on the 3 one, but remember that the 4th one is present, which is tags. So anyways, we read the file content, create blob object. This blob object is stored in .git/object. I'm repeating it because all of this is very essential and crucial to understand. And remember that this blob object is going to be compressed and everything. So once the object is created from the content, we're going to store the blob object in the database. By database, I mean the git objects part. So .git/objects. This is kind of like your database. And as I said, there's a particular format where you hash the thing, then you take the first 2 characters, create it as a folder, then the rest of the characters as the file name. And then the final thing is going to be the update index part. So we update the index to include this file. So pretty exciting. Let's get into it. The first thing that we have to do is, again, we'll have to create the full path. We don't have the full path with us. We are just passing in the path, which is this thing. So we create a full path, which is equal to self.path/file path or just path. After that, we check if not full path dot exists. Yes, we have checked this before, but I want to treat this as a standalone function. So if you're unit testing this function, this is the only function you care about. So if you pass in wrong details, like a path that does not exist, it is quite sturdy and does not depend on its parent function. That means this function add path. Parent function is like the function where this is called to do all of the checks. So a check is present here as well. And then again, we're just going to raise file not found error. So that's good. Path not found. Then the next thing is reading the file content. So to read it, what we can do is full path dot read bytes. We want to read it as bytes. So it opens the file in bytes mode, reads it and closes the file. Path module is, that's why like such a good thing to use. It's all very friendly as a developer. And now we want to create a blob object from the content. Now blob object will have to be created and then it has to be hashed. But there's a certain thing about how Git actually creates the blob object, how the hash is created. You have to arrange it in a particular manner. And that's why it would be wise to create it as a separate class of its own. So there will be a class blob that, has its own hashing function, has its own serialization function. So let's just create it at the top. And the thing is, I've told you already that this blob is a Git object. So what we're going to do is inheritance. We're going to create a class called GitObject, and then this blob is going to extend that Git object. And the reason we have to do it that way is because commit, trees, and blob all essentially have similar types of features. Everyone will have a hash function which calculates the SHA1 hash of the object. Then you have a serialization object so that, you can serialize the object to store it in the Git objects. By serialization, I mean compress the object and store it. And then you also have a deserialize function, which if given the bytes, creates a Git object based on those bytes. So we'll figure out how to do that. But essentially each one of them is going to have that feature. So that's why it would be wise to create a class called GitObjects or GitObject. And this will be the base class for all the Git objects. So like commit, trees, blobs, everything. And it is going to have multiple functions like hash and everything. And the sole reason we have all of those hash and everything is because Git uses a content addressable storage system. That means every object is identified by its SHA-1 hash. In real Git, they've migrated from SHA-1 hash to SHA-256 hash, which is more secure, but I'm just doing SHA-1. If you want, you can replace it with SHA-256. The way hash is calculated is also the same in every single Git object. They follow a particular format so that none of the details are missed. I'm going to talk about that, but let me just create init first. So we have a self here. Then we also get the object type. What type of object it is. Blob, tree, commit, what is it? And then we get content, which is in a bytes format. It's not in a string format. We get it in a bytes format. Remember that. After that, we have self.type is equal to the object type. Then self.content is equal to content. Great. After that, we have the hash function. And the hash is going to return a string. It's going to take in this content, which is bytes, and it will calculate the SHA-1 hash of this object. And the hash format is something like this. So you have the type, is it a blob, tree, commit? So that's the first thing you need to put in. After that, you need to put in the size of the content that's being hashed. After that, you put this / or \0, which is kind of like a null operator. You say that this is where like one part ends, and then you pass in the entire content that you have in a bytes format, and then you hash this entire thing. So it's like a function of this thing. Okay. So let's go ahead and create a header file or a header thing. Header is called this particular thing. So we have f, then we pass in self.type, then we leave space, then we have self.content, but we need to calculate the length of the self.content because that's the size. Then we put \0 over here and then call encode on it. And we call encode because, well, this is a string, right? We want to convert it in a bytes format. Now, if you're wondering why does Git do like all of these things? Well, that's because if you think about it, the details are not missed here. The type, it needs to be mentioned because everything is being stored in Git objects folder. Everything is going to be stored over here. How do you distinguish between commit, tag, blob, tree? How do you distinguish? So it's essential to put in this information in the beginning. Then you also need the size. What is the size? So that, the byte size can be extracted and displayed on the screen if the user goes ahead and types in git log. So that's a very important thing. And if you want, you can also use the size property to ensure that the self.content is not tampered with, because later on we are going to put content, right? So when you decode this hash, the self.content comes out, and if you calculate its length, is the same as this particular thing. So it can be useful there as well. But anyways, let's move forward and create a SHA-1 hash of this. So we have return #lib. That's what allows us to do SHA-1. Then we pass in the header, which is this particular thing. But then we also need to pass in the content. And to pass in the content, you just do plus self.content. And after this, you do hex digest. So it returns a digest value as a string of hexadecimal digits. So that will give us the entire SHA-1 hash in a string format. Great. Now we can do the serialization part. So given the content, we need to return the compressed version of it. So the content is in bytes, but we need to take this content, we need to compress it down, a lossless compression. That's very important, lossless compression, because we don't want to lose any data. Imagine like you compress and you lose one character. That's not what we want. So that's why we're going to use something known as zlib. But again, before we do that, we have to create a particular thing, which is the same thing as this one. We're going to have header. So we have self.type, length of self.content, this 0. Then we do return zlib.compress. Then we pass in the header plus self.content. And this will automatically compress and return us the bytes. Let's import zlib now. And it returns a bytes objects containing compressed data. That's very nice. So the serialization of the object for the storage in GitObjects is done. Hashing is done. The next thing we need is deserialization. So we essentially reverse this entire process. We use zlib to decompress what we have. Then we extract each of these things from here and return the Git object as it is. Pretty interesting, right? So let's go ahead and do deserialization where the self is there, and then we return the Git object instance. Now see over here, I'm putting it in a string format because I want to return Git object from the Git object class. If I return something like this, it will not make sense. The reason for that is Git object is not defined. The reason Git object is not defined is because you're within that class. How can it be defined? That's why what you do is put it in a string format called Git object. And Python is smart enough to realize this, that hey, the guy wants to return a Git object class, but he's within that class, but he still wants to return that class. So just make it happen. If you still want to use Git object like that, you can probably do something like this: from __ future import annotations. And then I think it is resolved. So that's like a new feature, I think, in some Python version. But if you want to be consistent with all the versions, you can probably do this. Either one of them should work. I think I like this from future import annotations. I'll keep that unless it gives me an error. Also, this should be a class method. So it's not going to return self to me, it's going to return class. And then we have data in bytes format. Now, why do we need this class method? Why can it not be the instance method? That's because you use this method when the logic depends on instance specific state. For example, we needed self.type or we needed self.content. So we do need instance of the class to access or to use this method. But in this method, we don't need the instance variables. We don't need any instance specific state. We don't need any of these functions, no need of these variables. All we need to do is take this function and apply the logic to the entire class, not a particular single object. And that's why it returns to us a class. We get access to this class because we might want to reference the class for inheritance or for alternative constructor. So we're not caring about an existing instance. We're caring about creating a new instance entirely. That's when a class method is very helpful. So anyways, let's go ahead and have a decompressed variable first. And that is going to be zlib.decompress. Then we are going to pass in the data here. This data we get is directly from the Git objects. So in Git objects, we have stored the compressed data. Now we want to get all the compressed data and decompress it. So this is like all the compressed data, we pass it in decompressed, and we have the bytes, which is actually technically similar to this content for a file, right? Because this content is decompressed content. Then it goes through this thing and it compresses it. Here we get compressed data, we decompress it, and then try to find self.type and self.content. So to give you a presentation, you can think of it like you have your original content file written out. Now you want to compress it because you want to store it in Git objects. So you compress it. Then you store it in Git objects. Now let's say you want to get the actual content again. Maybe you need the content because you want to determine what was the length or what was the actual content so that you can compare between two things or something like that. So when you do git diff, that's probably when this decompression will make sense. We'll see because we're going to use this deserialization. But yeah, so that's when you decompress. And once you decompress, you get kind of like this original file again. So let me just, do this. You just get the same file again. Very simple. Now we need to go ahead and find each of the things. So first of all, I want to find this thing so that I know that this is my length and this is my type. So I'll go ahead and file the null index. So we have decompressed.find, but we are searching in a binary string. Remember, this decompressed is in a bytes format. So it's not a string, and we're not going to bother converting it into a string. What we're going to do is search in that byte string itself. That's why I've put in B here. So it converts this into a byte format. Once we have the null index, we can find the entire header. So we have decompressed till null index. So it starts from the very beginning, goes on till null index. So it gives us this entire thing. After that, we have the content, which is equal to decompressed. Then we go from null index +1 till the end. Let me just do this actually. And with this, we have header, content, both of them. Now we need to get access to the object type, which is this thing, and self.content. How do you think we'll be able to get it? Quite simple. We have left a space here for a reason. And we have left that because we are just going to do object type and size is equal to header.split. And we're going to split it by a space. So we have a space here. We split it by space, so we get the type and a content. And split returns to us a list, right? So it automatically assigns the first element or the 0th index element to object type and size to the first indexed element. And with this, we can return a class. That's where the class helps us. It helps us create a new instance of this Git object. Self probably doesn't allow us to do this, right? Class does. And now we can pass in the object type and the size because that's what they require. Object type, not size actually. It requires content, sorry. So the size is kind of useless. We can just do this for now. So yeah, that's deserialization. With this, we have set up the entire structure for a Git object. Every single one of them, commit, blob, everything is going to be a part of this Git object, and it will be very helpful. You'll see how much time and code it requires. It saves us. So I create a blob now, which is extending a Git object. That's how you extend in Python. And again, this blob object is for the sole purpose of storing file content. A blob binary large object. So a binary large object. I think the name tells you what it is. So a blob will represent the actual content of a file in Git. It doesn't store the file name. It doesn't store the path. That information is stored in tree objects. Blob is just about storing the file content. And the way blob works is that, let's say you have two files with the same content. Let's say I had hi.txt and hello.txt, both of them with the same content. Hello world. The way blob will work is that it will create one blob object out of it. So it will have some hash, and we have already seen how we create the hash. That hash is here, like hash and serialization. So both of them will be created here. And then in the tree object, we are going to map this hi.txt to this and hello.txt to this. That's literally how it works. That's very efficient because there's no duplicate content stored in blob. So that's pretty cool. Now we can go ahead and do init. Now we have self, object type, and content. Now, if you're wondering, by the way, how I got that autocomplete, that's because of my extensions. I have many extensions of Python, so I'm not exactly sure which one, but Black Formatter is nice if you want to format your code. Python is also very nice, support for Python, obviously. And then Pylance is also very nice. So these three are like for sure recommended. So go ahead and install it if you want. And if you're wondering how on save it automatically formats everything, that's because I've set up settings to do that. You can check out ChatGPT or Google to find out how to do that. But essentially that's what's going on. And anyways, coming back to this topic, we have object type and content that we get from the constructor. We don't need object type from the constructor. We just need the content, and content is of the type of bytes. Object type, we already know it is blob because we are within blob, right? Obviously. After that, we are also going to create one function, get content. We have self, and then we return bytes from here. And all it does is that it returns self.content. That's literally a getter function that we're creating. Okay, so it gets the raw file content. Might be useful somewhere. We'll see. That's blob. Yeah. So now that we have created a blob object, we can go back to our add file. And here we have the file content. We have already created a bytes format of it. Now we just need to create a blob object. And for that, we know what to do. Blob is equal to blob. And then we'll pass in the content here. Great. So now that we've created the blob object, the third step is storing the blob object in our database, which is like the .get/objects part. How do we do that? Well, we can create a function for it because it can be a pretty complex one. So we can create a function for this. The reason we create a function is because it is a reusable function that we want to create, because we'll use the same function in add folder as well. Probably, or we probably use add file. We'll see. But either ways, it can be a very useful function. So let's just create it as a reusable function called store object. We have self with us, and then we have object, which is get object. Okay. As I said, I want to make it reusable. So I'm not specifically saying that it's going to be a blob that's going to be stored. It's going to be an object, a get object that can be stored. And as I mentioned, Git stores objects in like a 2-level directory structure. Given the object, it will try to find its hash. Then it will take the first 2 characters of that hash, create a folder. And then within that folder, it will take rest of the characters, name it as a file, and there we go. So anyways, we have object hash, which is equal to object.hash. After that, we have object directory, which is equal to self.objects directory / object hash, and then the first 2 characters. So this is where the directory is going to be. To give you a visual example of what I'm talking about, in objects, we saw 27. So that's what we have done with this line, object directory. Now we need to get the object file name or the file path, which is self.object directory, not self dot, sorry, object directory, this variable, followed by / object hash, then the 2 characters until the end of the content. After that, we can have if not object file dot exists. So if the file does not exist, in that case, we want to go ahead and first create the directory. And here we'll pass an exist OK is equal to true. That means, and then we write object file dot write bytes. So to this, we are going to write the bytes of object dot serialize. Now I hope you are getting a sense of what I was doing earlier. We had set up everything, but here we use the hash to give a file name and a directory name. And then we serialized it. We compressed everything to write to that file. And finally, we are just going to go ahead and return this object hash. Okay. We are still returning a string from here. The object hash is a string, and it will be helpful when we call store object. So let's go ahead and store the blob object in the database now. So we have blob hash is equal to self.store object. We pass in the blob. And now that we have stored the thing, now we just need to update the index to include the file. And for that, we'll have to edit the index file. So this was all about the objects part. We now have a new object being written to the .git folder. Now we just need to update this index file, this thing. We need to create a mapping. So as of now, if you notice in our mapping, the index is just like an empty map. We need to create a mapping between the file name or the file path and the blob hash, this blob hash. Again, I would like to point out the difference. Object hash is used everywhere. The object.serialize is just so that we have the compressed out content within that file. The unique identifier of that object is always going to be that hash. Okay? So we need to update the index such that the mapping is between the file path and the hash, not the compressed out version. So the very first thing we have to do to update the index is first load the index. So we need to know what the current state of index is, because index, think of it like a CRUD application. You have an index file where your data is written, kind of like a database. Now you first need to get the data from that database. Then you understand, oh, these are the files, let me update it. And then you store it back to the database. So that's what we have to do. So we're going to go ahead and create a function to load the index. And there are multiple or probably one edge case that we need to think about. So let's just create a separate function. It's also going to be reusable. We're going to use it everywhere. This is going to return a dict of string comma, I think it should be string. Let's see. And then we have from typing import dict. Make sure you do that. I like types. After that, we are going to do if not self.indexFile.exists. So that means if the index file that we had created here, if it does not exist, that means we need to return an empty dictionary. That probably should not be the case, but we're just handling an edge case here just in case, the user deletes it or something. So we just return an empty dictionary. Otherwise, what we try to do is try except. Why? Because we are going to do JSON handling here. And also if we get an error, we are just going to return an empty dictionary. If you want, you can print out an error message, but that will be visible to our user. So tread carefully. After that, we are going to have return.json.loads. And here we want to load what? Well, first we have to read the index file, right? So we have to load the content that's present in the index file. And to do that, we can do self.indexFile.read text. Remember, we are reading the file in text mode. We are not reading the file in bytes because we are not going to store it in bytes format. We have a dictionary. So it's like kind of like a English thing, but the value is in bytes format. But we do want to get the value present in bytes format with its actual string, like if it makes sense. So first we'll just do that. Also, I have to probably mention the indentation here. Indent is equal to 2. I'm not sure if it accepts 1, so I'll just leave it. I think it will automatically infer, but yeah, let's go ahead and call self.load index, and we have an index with us. So let's save it like this. After that, we need to create a mapping. We have a dictionary with us. Remember that. So now we need to update it. So we have index at file path. And where is our file path? Well, our file path is this path. So index at this path is equal to the blob hash. So you know how this would work. If we have an empty dictionary, it will add that hello.txt file or any file you mentioned, followed by the hash that's present. And this hash is also a string. Cool. So we have updated it. Now we need to save it back to our database. So this was loading, this was updating, and now we want to save it again. So we'll have to create a function to save the index, and then we'll pass in the index. This is the dictionary, okay? Now we can go ahead and create a function called save index. And this should be quite similar to this thing. Self.index file dot write text json.dumps, but here instead of getting an empty dictionary, we pass in the index as a dictionary itself. So we have index dictionary string comma string. Take this index, pass it in over here, and there we go. So we are writing to the index file by JSON-ifying it, if you want to call it that, like converting it into JSON. Also, now that we have done this, let's just go ahead and init. Within init, we can just do self.saveIndex, and we'll just pass in an empty dictionary. Let's remove this. We're writing clean code. Now we can take this self.index and save it here. That seems right. After that, we can just say print if added the file underscore path or added path. Both should be fine. So yeah, that's add file. Now we also need to add support for add directory. So what I'm going to do is just add directory here, self, and I'm going to create it as a placeholder function so that it doesn't give us any error. And I want to test out the functionality of add file, because directory is going to be quite similar to add file. There are certain edge cases, but the logic is quite similar. So if add file works, we can be sure add directory will also similarly work. So let me just test it out. So we have add main.py. I'm going to open the file explorer so that we see it in real time. Everything's expanded. Then we click on enter and it says added main.py. If you notice, B878FD236C29, this entire thing was added and it's in a hashed or in a compressed format. And now if I go to index, we have a mapping. We have main.py, which is pointing to this particular thing. Now notice, I'll again do add main.py. It adds it, but there's no visible difference. And the reason for that is because the content within main.py has not changed. If the content does not change, it will return the same hash to us. And this is a very important trait because we'll use this in git status when we want to understand what's the current position of our system, what needs to be staged. So like what files are essentially untracked, what files are in the staging area, and what have been committed. That's what git status tells us. So this will be very useful because if main.py has not changed, it has not been modified, it will be the same. So you don't have to, update it anymore. To give you an example, let me cd out. We have git status. On branch main, no commits yet, changes to be committed, and it says new file, hello.txt. It needs to be committed. How do we know that? Well, it's in the staging area. That's how we are going to know. Untracked files, hi.txt. How do we know it's not being tracked? Because it's in the working directory, but it's not present in the staging area. And after I commit this hello.txt, you'll notice that this will be removed. But then if I update hello.txt, it will say that, hey, this needs to be added to the staging area and needs to be committed because it has been modified. So like all of those things are very dependent on this hash returning the same result for the same content. So that's very nice. Now see one thing. Once I add this add directory, I'm again going to do git add main.py, and you'll notice this hash will change then. I'll just show you a small thing. I'll just add a hash over here. So I've changed the file content. I'll go to index and let me add main.py. You noticed? That's the thing. The entire hash changes. Now, obviously, we are not adding support for garbage collection. Garbage collection is essentially like, you notice that we have two objects here, but only one object is actually being used. So, we should remove, let's say, this B8 thing because it's useless to us. It's not being used in the index. It's not being used anywhere. So let's just, remove this unnecessary thing. It's not required. Well, that's garbage collection. We're not adding support for that, but that's something you can figure out on your own how to do. Okay. So again, I'm going to run main.py. Again, we are back to our B8 thing. That's good. And just so that we don't have a lot of objects, I'm going to delete it. Okay, great. Now let's go ahead and add support for directory. Now if I try to add support for directory, nothing will happen. It won't give us an error because, well, good thing is, well, it gives us an error. Add directory takes one positional argument, but two were given. And that's because we have not taken a path. So let's just take a path here and add support for add directory. As I said, add directory should be like recursively reading from the directory. So if there's a directory within a directory within a directory which has files, it should read all of these directories, get all of the files within all of the directories. That's recursively reading the directory. So the first thing we want to do is we want to recursively traverse the directory. Now, once we recursively traverse the directory, we will get the file. Now, for each of them, we want to create blob objects for all files. Then we want to store all blobs in the object database, or object database is essentially like my .get/objects. All right. I'm just calling it a database because like I want you to feel like it's a CRUD application where our database is locally stored. And then we update the index to include all the files. Okay. The only new step is recursively traversing the directory. And now instead of one file path or one file, we have multiple files. Should not be that complex. So let's start off by adding the check of this thing, path not found. So full path is equal to this. If this does not exist, path, or let's say directory, because we are saying that, hey, we recognize this as a directory, does not exist. Then we'll also add if not full path dot dir or is dir. That means it's not a directory. Then we raise a value error of if directory path is not a directory. And what is a directory path? Well, it's just this path. So let's just add it. Okay. So let's go ahead and recursively add all the files in the directory. So we need to recursively do it. And to do that, we can just do full path. So this is the full directory's path. Then we do .r_glob. So it recursively yields all the existing files of any kind, including directories, matching the given relative path anywhere in the subtree. And then we pass in asterisk. That is the pattern. Asterisk means we get everything that's present within this folder. And then we need to recursively go through it. So like we go through a for loop, because our glob will return to us a generator. That means we need to iterate through it. So we can just do for file path in this. We are going to go over and check if file path dot is file. If it is a file, then what do we do? Well, if it is a file, then we want to create the blob object and update the index. So let's go ahead and create blob object and then create index or update index. So to create a blob object, all we need to do is blob is equal to blob or blob. Then we pass in the content, which is this content. Now, how do I get access to the content? Well, I can just do content is equal to file path, right? This is the file path. So if I have access to this file path, I can just do read bytes. So I have content with me now. I create a blob object out of that content. And then it's pretty much the same thing as before. We just create a blob hash. So we self.store the object by passing in the blob object here. And then we update the index. Now to update the index, first we need to get access to the index. And what I'm going to do is outside the for loop, I'm just going to create an index variable. So index is equal to self.load index. The reason I'm doing this outside of the for loop is because think about it, for every file we need to do this. Why do we have to do that? We can just load it once and then the index can be updated within this code. So we have index at the path. Now what is the path? Well, we need to get the relative path. Remember that this path that we have is an absolute path. It's not a relative path. So we need to get the relative path out of this, and to get the relative path, we'll have to use some logic. And I'm going to create the relative path here because there's some additional edge cases that I'm missing. So I'll explain what those are, but first let's get the relative path. So we get the file path, which is this thing, relative to what? Well, the directory we are in, which is self.path. Remember that? This thing that we have at the top, self.path, the current directory we are in. So what is the file relative to the directory? So we take this relative path, put it as the key, and the value is going to be the blob hash. After that, well, we are essentially done. So once all of that is over, the entire for loop is over, we can just do self.save index and pass in the index. So we load the index first, we go through every file that we get, we check if it is a file in the first place. If it's a directory, we don't want to store it. Then we get the relative path, we create the blob object, we update the index to include that blob object. By creating the blob object, I mean we also store the object. So create and store blob object, and then we save to the index. But there are certain edge cases over here. The very first thing is, what if I do python3 main.py add full stop here? What is going to happen? That means it's going to add every file it can find within this git clone. That includes this .py git file. So it will go through this file folder, it will go through this folder, it will go through this folder, it will take this file, add it. The same happens for refs, heads, head, index. Every single one of them will be added. We don't want to do that. So how do we avoid it? Well, here we can just skip the pygit. So if this .pygit is in the file path .parts. What is parts? Parts means an object providing sequence-like access to the components in the file system path. So that would be like, then we can just simply continue. So if that is a part, we continue. We don't want to go through this. We skip the pygit directory and its contents. And now that I realize relative path is probably not needed at the top, I can just use it over here. The reason I did it above earlier is because I had an edge case in mind, but that would probably cause bugs. So I'm removing it. No, I won't tell you what it is so that you don't get confused. I think this is good enough for us to understand. Now, once we have done that, we also want to tell the user, hey, these are how many files we have added to the index. And for that, we'll have to keep track of how many files we add. So we have added count is equal to 0. And for every successful one, we are going to do added count plus equals 1. Then we can check if added count is greater than 0. We do print added count files from directory, and then I pass in the directory path. The directory path is just the path. Otherwise, we can say that the added count was 0. So we can simply say the directory path already up to date. Cool. So that is the entire logic for add directory. Let's test it out. We can just do add full stop, and let's remove the object from here. Index will automatically update, so I don't think we need to care about that. And well, done. Added one file from directory full stop. And if we go here 24b, yeah, that looks good. So yeah, the entire thing works out. If you want, it also ignores the .py git. If you want, you can create a separate test folder, try it out, I'm pretty sure it should work because the current directory worked. Everything else should work. So yeah, that's about the add part. Let me remove all of these things. So that's the support for git add. The next thing is git commit. And this can be a bit tricky one because we are going to have trees, we're going to have commit objects, all of those created, and well, it is going to get a bit tricky. So stay with me. It's not difficult, but it is a bit complex. There's multiple moving components. So let's get into that. So first things first, we're going to add support for this commit command here. Let me go ahead and add the comment of commit command. After that, we are going to create a commit parser, which is equal to sub parsers dot add parser. After that, I'm going to add the commit here, and then the help message is going to be create a new commit. Nothing fancy. After that, we're going to add an argument. Whenever you do git commit, you do git commit -m, right? And then you pass in the message. That's exactly what we want to do. So I'm doing commit parser dot add underscore argument, and then I'm going to pass in -m. That is going to be the argument that you can specify. If you want, you can also have -- message because -m stands for message. Both of them can be used. So git commit -m or git commit -- message, both are fine. And then you can specify the help message, which is, well, commit message. After that, you can also specify that it should always be specified. If it's not specified, it's going to give an error. Cool. After that, we are also going to add an argument for author. So when you pass in the commit, you can also specify what author it is. Now, generally no one uses it or no one does it because Git already has support for, global configuration of the user. So let's say you're talking to GitHub, for example, you have to specify your credentials over there. You have to say who you are, like what's your email, what's your name, etc. So there exist Git commands to do that. Now we're not adding support for those, but here we are adding support for -- author. And here I'm just going to say author name and email. But again, this is not going to be required. And as I was saying, this is done generally globally in the system. So if you want to check out your Git configuration, what you can do is cat.gitconfig, and it should work out for you. You can click enter and you'll get your name and email being used. Of course, you need to be in the root folder. That's where it is. It's not in the desktop folder or anywhere else, just the root folder in the .gitconfig file. Cool. After this, we are going to go ahead and add elif args.command is equal to commit. If that is the case, then again, we are going to run this if condition. So the if condition is if report.git directory does not exist, we're just going to return an error message kind of that, hey, you're not in a Git repository. But if it is present, then we want to do repository.commit. And we have to create that function. Also, we need to decide what things we're going to send in here. First of all, I want to send in a message, which is going to be in args.message. And I'm sure this message is going to be present because you remember I've done required is equal to true here. So obviously args.message is going to have this thing. And also one thing I probably did not tell you before, so I'll tell it now. The thing is, whenever you specify add arguments like this -m, what you can do with that is git commit -m and then pass in the value. So what is the value of this git commit going to be? I mean, what is -m going to carry as the value? So args.message actually carries the value that you pass in over here. If you think about paths here, this is also add argument paths. And here we don't have any hyphen or anything as such, but if you don't specify it, it will automatically think that, hey, yeah, after add, whatever we have goes under paths, and that's how it was able to work. But with this, we can explicitly say that -m or -- message when specified is going to get a value over here like this. Okay. I think even if we do this after that, it should work fine. Not totally sure. But whenever you do arguments, you can do -m equals this or paths is equal to the values and it should work. But yeah, that's it. Now we are sending the message to this commit function, but we should also be sending in the author, correct? So here I'm going to create a variable for args.author. The reason I've created a variable is because there can be two values here. The args.author is not a required value. That's why here I'm going to say if args.author is specified, we're going to use that. Otherwise, we're going to use the user called pyget_user, and then we're going to specify the user like this, user@pyget.com. Well, yeah, doesn't sound that bad. After that, we're going to save it. We're going to create a function for commit now. So here, let's go ahead and have def commit self. Then we're going to add the message. And if we look down, we are sending the message and followed by the author. So here we are going to have message, which is going to be a string, and then the author, which is also going to be a string. And if it's not specified, well, it should be specified. We have handled that condition, but still, if it's not, we're going to have pyget_user, user@pyget.com. Yeah. After that, we need to figure out how the commit process works exactly. So yeah. Now, how does commit work? Well, for that, again, we'll go to our git test folder. I'll clear everything off so that we have a fresh start. Then let's go through again what's present in .git cd.git and then ls here. Let's see. What I'd like to do here is go to this objects folder. So we have ls objects. So as of now, we only have 27, which is the one file that we've added. And just to revise what we've added, we can just do git status. And we have added hello.txt. Now what I want to do is commit. So I have to specify the commit message, and then I will see how this changes. We are going to implement this later on, so we'll see that. But we'll also see how the objects changes here and how the index changes. If you remember, index had some value in it, right? Yeah, I would like to cat the .git index. This is how it looks like. Cool. Now I can do git commit -m, and then I specify some message. So let's just specify some message. Cool. It says one file changed, one insertion, create mode 100644. So whenever you insert a normal file, Git automatically gives it 164 mode. And if you did do it to a directory, it's probably going to be like 400,000. We are going to implement that as well. But now if I go to cd.git and then go into the ls objects, now we see we have 24, 27, 94. So we have a new two set of objects created. Why are these two set of objects created? To understand that, first we need to understand what exactly does a commit do. Well, we saw that from working directory to go to the staging area, what we did is git add. To go from the staging area to a local repository, that's when git commit comes into play. So here what happens is that the data within the staging area goes from this place to this place. And what happens to the things that are present within the staging area? Well, to see that, we can just cat the index, right? If you see, hello.txt is followed by tree1 or something like that. So that's how the real Git processes it. For us, it's going to be much simpler. We are just going to wipe off the entire index file. So every single time we move from the staging area to the local repository, so we have something that's created here, we take that entire thing and push it to the local repository. So what we're doing is essentially whatever we have in the staging area, we're creating a snapshot of it so that it doesn't get overridden by any of the changes we make later on. That's a commit. It's essentially a snapshot of your current staging area. And you set up your staging area by adding files to that staging area from working directory using git add. As we noticed, there's an index file in the staging area. We need to take that index file, process it somehow such that we create a snapshot of it and store it in a local repository. Now, how do we convert that JSON thing that we have in index file? If you don't remember, this is how our index file looks like. It's like a JSON file. How do we take this, convert it in a form such that, it's a snapshot looking kind of thing and store it? That's where the concept of trees come in. So as I told you before, there are three types of objects we are going to look at, right? Blob, we already looked at it. Commit, that's what we are going to look at it right now. And then trees. This tree is essentially what we are going to create from the staging area to send it into the local repository. So the JSON file that you notice, this main.py entire thing, we're going to create a tree out of it. Why do we have to create a tree? That's because we want to create a hierarchical structure. Why do we want to create a hierarchical structure? That's because right now we only have main.py. But let's say I had some folder here, let's say a test folder. Within that I had hi.txt. Within that test folder, I also had another folder called test2. Within that I had hello.txt. Let's say I added all of these files within the index, correct? Now the issue here is that the index is only going to look something like this. It's going to contain test hi.txt, then there's some hash associated with it, followed by test2 hi.txt, and then some value associated with it. The problem is this is linear. There's no hierarchy established as such. So what we want to do is that everything that's present in the test folder should be within the test folder. So we take this off and we do test. Within that we have test2. Within that we have hi.txt. So we want to create a structure that looks like this. And then we are going to have hello.txt here. I think I've messed up. This should be hello.txt and this is hi.txt. But you get the point. This is the kind of structure we want to establish. A hierarchy where relation is clearly established. Test has a folder of test2 which has a file of hello.txt. Once this relation is established, we can just pack everything together and send it as a commit snapshot. That's why we have to create a tree. Okay. Now, once we create a tree, we'll have to create a commit, but I'll get to it later on. That explains why we have three objects here instead of one before we did git commit. One of them, either 24 or 94, is a tree and another one is commit. So commit is also an object, right? If you remember, here I specified commit is also an object. So that is also stored in .git/objects. So we also have to create a commit and that commit contains the tree hash. As we had the hash and serialization in Blob, we also have the hash and serialization in trees and commits because that's where we established everything, correct? We established all of that in GitObject class, the super class of everything, the parent class of each and every one of them. That's why. So having understood that, we're going to go ahead and divide how this new commit is going to work. The first step that we have as of now is that we want to create a tree object from the index. So we want to get it from the staging area. For this, I'm going to create a function because this is a fairly complex one and you'll have to pay a bit more attention to it. So we have def create tree from index. That's the function. Then it's going to be a self and let's have a pass. Then I'm going to call this function here. So we have self.createTree from index and what this is going to return is a tree hash. So what we are going to do in this function is that we are going to fetch the index. We're going to create a tree from that index. Then we are going to store it in the .git/objects. After we store it, we are going to get a tree hash, right? I mean, tree hash is the way we are going to store it because as we know, the file name is the tree hash. So we are going to return that. If you want, you can pause and give this a shot yourself. The code doesn't have to look exactly like mine, but it's a good thinking process, kind of a lead code kind of thing. If not, let's go ahead and do it ourselves. I'm going to minimize this explorer, and here the first thing we want to do is load the index. So we have index is equal to self.load index. Now we have a dictionary with the index. The first thing I'll do is that I'll handle an edge case. If the index is empty, in that case, I'm just going to return something like a tree object. And then I want to store this tree object. So I'll just do return self.store object and pass in the tree. So store object is a reusable function as I had mentioned before. Then we have an object of GitObject. Tree is what we are going to create now, which is going to extend GitObject. So let me go at the top and create a GitObject. I'll create it after blob. So we have class tree GitObject. So here we are going to have an init function. And in the init function, we're not going to take object type. We're going to take in the content, but content is not exactly given to us. Because here's the thing, tree object, what does it represent? We need to understand that. So the tree object is representing the directory structure. And what is a directory? Directory contains the files. And what does each file have in them? Each file is going to have an associated permissions thing. So what permissions does each file have? After that, it's going to have a name. So what is the file name or the directory name or whatever? And then it's going to have a hash associated with it. So it's going to be the blob, right? Because if you remember, how are we storing the content of each thing? We're storing the content by using a blob, right? So each content is going to be three things. It's going to have a mode, which is the file permissions, as I mentioned. Then it's going to have a name, the file name or the directory name, whatever. And then it's going to have a hash associated with it. And that hash is going to be the hash of the blob. That's one thing. Or it can be a hash of another tree. When is it going to have a hash of another tree? Well, when it's going to be a folder. Because think about it. Test is present. We have a file hi.txt here. That is going to have the blob content directly. Because it's a file, it can contain information. But if it's a folder, it is going to point to another tree, hoping that it's going to contain the blob hash. So it can either be a tree hash or a blob hash. And if you know anything about recursion, this is a classic recursion problem that we are going to encounter. So each folder can have a folder or a file. If it's a file, it can be a blob sha1, or it is going to be a blob sha1. And if it's another folder, then it's going to point towards another tree. And in that another tree, we can have another file or a folder. And if it's a folder, we again have a hash pointing towards another folder. But if it's a file, then here we have the sha1 hash of the blob. Now, if you don't understand it, totally fine. I'll draw it out later on once we have the code so that I can help you visualize it. But anyways, here we are going to have multiple entries, and it's going to be a list of entries, and each of this list, let me just import from typing import list, and each of this list can have three things. It can have a mode, which is going to be a string. Mode tells what the file permissions are. As we saw, 100,644 was the permission for a regular file. 400,000 is for a folder. That's the major two we are going to deal with. Then we have the file name, which is also going to be a string. And then finally, we are going to have a hash. And hash is also going to be a string. Now, obviously, a list cannot have three arguments here. That's why we are going to use a tuple. And also, we're not using a list again because this is going to be immutable. Tuples are immutable. Lists are mutables. That's why we're using tuples. These three values will never change. Also, let me just use tuple from typing. After that, we are going to call super.init, pass in the tree. That's the object type. But the content, we can't directly pass in this entries here, right? That's because the content here is of the type of bytes. Entries is list of tuples. That's why what we need to do is serialize these entries. In Blob, it was quite simple. It just followed what the get object said. The serialization is as follows. But in our case, we'll have to have one additional step before we can send it to this serialization because it requires content. And in our case, the content is not present. So we need to convert it in a form where content is bytes. So here I'm going to create a function. Let's call this def serialize entries self. Then we are going to return bytes from here. And the format here is going to be quite similar to the ones we've already seen. The format is going to be something like this. We have mode, then we're going to leave a space, then we're going to have name, what's the file name, followed by \0, and then we are going to have the hash, the object hash. Cool, quite straightforward, but the only problem is this is a list of tuples, so we have to iterate through it. So we'll have for mode, name, object hash. Notice I've called this object hash, not blob hash or tree hash, because it can be both of them. It can be blob hash or tree hash. After that, we are going to call sorted here self.entries. Also, I need to create a variable called self.entries, which is equal to entries. And if it's not specified, then we are going to use an empty list. So if entries is null, it's going to use an empty list, just so that entries is always a list, not a none value or anything. Otherwise, this function will give an error. Also, why are we sorting this? We are sorting so that we have consistency. What do I mean by consistency? Let's say our entries were hi.txt and hello.txt. So you put in hi.txt first, and then you put in hello.txt. So that gives us one hash. But let's say in another thing, in another commit message that you're trying to create, you add hello.txt first and then hi.txt. That will give us a different hash. So our git clone is going to think that, hey, the files have changed, something has changed, so we are able to commit the same files again, and we don't want to allow that. Sorting gives us the consistency that hello will always be first because he followed by hi. So that's the consistency I'm talking about. The order does matter over here. After this, what we can do is create a content variable. Let's call it content is equal to b. It's going to be a byte string because the object hash that we're going to store and the mode and name that we're going to store, everything is going to be a byte format, right? So all we're doing is content plus equals f, then we pass in the mode, then we pass in the name, followed by \0 dot encode. So we have created this as a byte string and we have added it to this content. And we are doing this for each and every single one of these entries. After that, we can again do content plus equals bytes dot from hex. The reason we have to do from hex over here is because if you remember, the object hash for the blob storage or the get object in general is always going to be hex digest, right? Return the digest value as a string of hexadecimal digits. So we need to convert that hexadecimal digits back into the bytes format. So bytes.from hex needs to be done. And then we can pass in the object hash. Again, we are only doing this because here we are done .hex digest. So it gives us a hexadecimal for each of the get objects, and each of the get objects includes blob and tree both. So with this, we have the content ready. So we can just return the content after this. Cool. We have the serialized entries with us now. So I can go ahead and have content is equal to self.serialize entries. Then I take the content, pass it in over here, and we're good. Now there's another thing that we need to add to this tree, and that is the add entry function. So here we have an entries, which is a list of tuple. I've already explained this to you multiple times, but essentially in this tree, we want to add the support for adding an entry, right? Let's say we have a structure like this. We have test folder. Within that test folder, we have hi.txt, but after that we have test2 folder. Within that test2 folder, we have hello.txt, correct? Now, obviously this is not a binary tree, mind you. This is a tree that can have multiple children. So what if we want to add another child to this tree? That's why what we're going to do is a function called add entry. Then we're going to have a self. Then we're going to take the mode as a string. Then we're going to take name as a string, then the object hash as a string. And well, they're going to be very simple. We're just going to do self.entries.add or append, I think. Yeah, that's how lists work. So we are taking this entries list and appending to it. And then we add mode, name, and finally object hash. But now since the entries has changed, we also want to ensure that the entries are serialized, correct? So we are going to re-serialize since the content has changed. So let's do self.content is equal to self._serialize entries. I hope this makes sense. In the init method, when we add entries, we serialized it. So we have content here. Now, similar to the GitObject function, we also need to create a deserialize if we create a serialize, right? If this is like encoded in a certain fashion, we want to ensure that we can decode it. So we're going to follow a very similar pattern. We're going to have @class method. So we have @class method called from content. Let's not call it serialize, deserialize or whatever. We're instead calling it from content. So given the content bytes, we're going to create a tree from that content. So similar to this deserialize method, if you remember, the content is taken from the working directory or whatever, then it's passed in, then we have a blob created, which is stored in the Git objects. Then we deserialize, and then we again come back to the original thing. So what's happening here is that from the serialized thing, we were deserializing, and the same thing is happening here as well. But the process is going to change a bit because we are not using zlib to decompress here or to compress in the first place, right? All we're doing is like simple addition. So we can figure that out here. Also, we are not going to return get object. Instead, we are going to return a tree. After that, we're going to create a tree is equal to class here. Then we are going to have I is equal to 0. Then we have while I is less than the length of the content, and the content is mentioned over here. It's given to us as bytes. So while I is less than the length of content, so we are looping through each and every bit or byte, whatever, of this content. What we are going to do is null index is going to be found out for that content.find. Also, since this is a byte string, we are going to do b/0 or \0, comma I. What this does is that it finds the null terminator because content will look something like, something like this. So it looks for this \0, and this I is basically from where the searching should start. We should not start from the start, right? Because if we start from the start every single time, it's going to find the same /0. Take for example, we have thing that looks like this. For example, 10644 or 100644 followed by readme.md. Then we have \0. Then we have 20 bytes of content hash. So the reason we have 20 bytes of content hash is because we are using SHA-1. It's always going to like give us a 20 bytes of content hash. And then we are going to have, let's say, some other file. So this is how it's going to look like. So what we are doing is finding /0 here, and we only start from where I is. So let's say I is over here. It only starts from here. Once we have found this out, we can go ahead to the next one so that this is never encountered. If we don't put this I, what's going to happen is that, let's say we are over here, we found this, correct? In the content, we did find this because find returns the first index that it finds. It returns the lowest index in B where subsection sub is found. So it will always find this, and that's not what we want. So we always start searching from I. Cool. After that, we're going to check if the null index is equal to -1. If it is equal to -1, that means there's no \0 found in the content. If it is not 1, in that case, we need to pass the mode name. So we have mode name is equal to content I till null index. And we are going to call the decode function on it because, well, this is bytes. We want to get it in a string format. So once we find \0, we have these two things, mode and the name given to us. Then we're going to split it apart so that we have mode comma name coming in after doing mode name dot split, and we're going to split by a space. The max split that we can do is 1. That means if we have more than one space that it finds, it will only do the first set of splits. For example, let's say if we had a string of hi, 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 and we called split on them, let's say doing this, the output will only be hi and hi. It will not go through and split the third hi. To prove it to you, I've put this code in Python interpreter online. And if I run this, you see we get hi. So that's the very first string. And these two are treated as one single thing because it only splits by this first space. Once all of that is done, we need to extract the object hash, which is equal to the content from null index plus 1 till the end. And actually not till the end, because if you think about it, we are in a while loop. We are continuously finding one element after another. Because let's say this was one file, then we have another file, then we have another file, then we have another file. So if we do content null index plus 1 till the end of the file, what it will do is that from here, the first \0 that it finds, it will grab everything from here. We don't want everything. We just want this hash part. Then we can go into the while loop and carry out the rest of the techniques. That's why what we're going to do is here, we're going to put in null index plus 21. And then we're going to hex it out. Because obviously, object hash even before was a hexadecimal string that we created. Now, why are we doing plus 21? That's because we are guaranteed to have 20 numbers or 20 characters in that hash string. That's how it works. SHA1 hash gives us that. And after this, what we can do is tree.entries.append, and then we can pass in the mode, name, and object hash. Once this is done, we can set I equal to null index plus 21, correct? Because we are going through every character one by one in this content. Now, if we go by every character, that means we're at I is equal to 0. Let's say we are on the first mode, which is 100644, for example. So it goes through 1, it finds the null index, then it carries out all of these operations. And if this was not present, what it would do is that it would go to I equals the next thing. So now from 0th index, we are now at first index. Then it will again find this \0, recalculate it, and that's bug. So that's why we are doing I is equal to null index plus 21, so that after the first thing, we directly move to this particular part, or actually I think it's this particular mode. So the next mode entirely, okay? Once all of that is done, we can return the tree. So yeah, this was great. We created a tree now from the serialized content, and this is going to be a very, very helpful method to us. You'll see that in the commit function itself, I think. We pass in the content, which is the blob or whatever, and then it will give us out a tree created from that blob, for example. And this is such a good thing because we are going to use this in the commit itself, in the commit function. So whenever we have another directory present, we are going to call tree.fromContent, pass in the content, and everything will work out, you'll see. So coming back to the commit function, here we only have a tree hash as of now. And actually we need to be at create tree from index because we are creating a tree. Now we have handled the edge case. We now have a tree and it returns an empty tree, or it stores an empty tree just in case the index is empty. But what if the index is not empty and we do have files within the staging area? So that's why what we're going to do is group by files and by directory. So as I had mentioned, we're going to convert this index into a more organized dictionary. And from that, we're going to create a tree. So we're going to have two things. We're going to have directories, and then we are going to have files, both an empty dictionary. After that, we're going to go through every single file within the index. So we're going to have for file path, comma, blob hash in index.items. So the index has this and this. So we have file path and then the hash. And now what we want to do is group by the directory, right? What directory are we in? Based on that, we want to group it. Now, how do we realize what group one thing is in? Well, we know hi.txt and this particular thing, test2 /hi.txt, are in one folder. How? Because their first part matches. The thing before the first forward slash matches. So whenever the thing matches after the first forward slash, it means they're in the same group. So here we are going to do the same thing. We are going to create multiple parts and the file path is going to be split by the forward slash. After that, we are going to check if the length of parts is equal to 1. That means file is in the root folder. So in our main.py case, file is in the root folder, correct? So we only have one part where we are just going to say files at parts at 0 is equal to the blob hash. So essentially we are recreating what we have over here. Main.py is the parts at 0. So files at main.py is going to be the blob hash that's associated over here. But the difference comes in when the file parts is not equal to 1. That means the file is in subdirectories. And that's why what I'm going to do is get the directory name first, which is equal to parts at 0. Then I'm going to initialize that directory name within this dir's thing. So as of now, it's empty. But now I want to create a map such that, we have something like test with an empty dictionary within it. So once we have an empty dictionary here, I can go ahead and initialize test2, have an empty dictionary. And after that, finally, I can have hi.txt or hello.txt, whatever we had, followed by the hash. That's the entire thing I want to do. So the first thing I have to check is that if this directory name is not present in the dir's folder, in that case, I'm going to do dir's at directory name is equal to an empty dictionary. Now I want to store the nested structure. So I'm going to say that the current thing that I'm in is equal to the directory at directory name. So stay with me. What we have done here is that we have test. So we have test here. We've created an empty dictionary at this point. Now what I'm saying that current is this particular dictionary. Now I have access to this particular dictionary. And now within this, I want to create the same structure as before. I want to pass in values. But the thing is, I don't know how deeply nested it is. Here it's very simple, but what if we have test3, test4, and test5? I don't know how many subfolders are present. And that's why I have to use a more dynamic approach now. So what I have to do is for part in parts from 1 to -1, which is towards the end, I'll have to do if part not in the current. So that means, let's say this test2 that is not present in our dictionary here. So I'll have to reinitialize it. Essentially this part. So we have current at part is equal to an empty dictionary. After that, I can just do current is equal to current at part. And I keep doing this until we get to the end. The reason I've done -1 over here and not this is because if I do -1, it will skip the last element because that's how Python indexing works. The list slicing works in a way such that the first index is included, the last is not. So that means the last element will not be included, and that's exactly what I want. And the reason for that is because once we get to the last part, we are out of the for loop and we do current at parts at -1 is equal to the blob hash. I hope that was understandable. Definitely a bit tricky to understand, but let's go over it again. Instead of explaining it like this, let me go ahead and just copy this function, paste it in the online Python interpreter. Let's run this and somehow the code executes, but that's fine. Here I'm going to pass in the index. What we need is our index that looks like this. Run this now. So I'm going to have create tree from index. Let's remove self and we have create tree from index like this. Well, no error. That seems like a good sign, but let's go ahead and return, or let's print the dir's and the files. Yeah, that's what we have. So let me just print it out on a new line. So we have main.py as a file which is present here. Then we have the directories. So within directory, we have a test file, or not a directory, but like another file called hi.txt, followed by another directory, which is test2, followed by another test3, test4, test5, then hi.txt like this. So it does work out, but why does it work out? Well, that's because file path.split splits everything. So we have test, test2, test3, test4, test5, hi. Okay. Now, if the length of parts is equal to 1, well, that's not the case with this particular thing, right? It was true for main.py because main.py is in the root folder. If you do main.py split by /, there's no /. So it's going to return this main.py as a whole, and it's going to be in a list, but there's only going to be one element in that list. So now if the length is not equal to 1, then we go over here. Then we get the directory name, which is parts at 0, this test folder. Then we create a dictionary. So we have a dictionary that's something like this. We have test like this. Okay. After that, we put in a dynamic logic. What we say is that from this particular path, the test2, we are skipping the first element. We are directly starting from test2 and we go until test5. We are not going to hi.txt. We are not going to the file. We're just iterating over all the folders that are possibly present. For each one of them, we are adding test2, test3, and so on. And finally, when the for loop is done, so we go until this test5, we get out of this for loop and we do current parts at -1, which is the last element, which is hi.txt, is equal to the blob hash. And that's how we get our value. And that's how we have, let me just update the index, by the way, that's incorrect. And that's how here we have the value correctly spitting out. Cool. Now we know that the directories and the files are present individually. I want to concatenate both of them. And for that reason, what I'm going to do is create a variable called root entries, which is equal to a dictionary with all of the files present. I've put in 2 asterisks here because I want to decompose the dictionary. We have a files, which is a dictionary, but I want to take this files list. And essentially, if I do this, let me just, give you a visual demonstration. And then I do print *** hi. Well, obviously it gives an error because this has to be within a dictionary. Then if I hit enter, we get the same structure. So that's what we are doing. We are taking the files and we are essentially melting it down into its components and putting it into a dictionary. Now, why are we doing this? Because we are going to create a root tree. Now what we are going to do is for the directory name that's present and for the directory content that's present, we're going to go over each one of them, each one of these directory items. Let me go back. So for each one of them, each one of these things, what I'm going to do is root entries at directory name is equal to the directory contents. Cool. So now everything is in one dictionary. To prove it to you, I'm again going to copy paste all of this within this thing. So we have stuff like this, and I'm going to print out the root entries. And there we go. Everything is in one single dictionary, even the main.py file. So all the individual files, all the directories, both are in root entries. And the reason we have to do this is because we are going to create a tree out of this. We can't pass in 2 dictionaries, correct? We have to pass in a single dictionary to create a tree out of it. And here, how do we create a tree? Well, it's a classic recursion problem, as I said. A tree can either point to a blob hash or another tree. So let's say you're from the tree's perspective over here. Now, what can this tree do? It has 2 options. I can either point to a blob, which is the file content, or I can have another tree. And then this recursion goes on and on. This tree also has 2 options, either a blob or another tree. And in our case, that's going to be the issue. We are going to have test2, which is going to point to a tree. Then test3 is also going to point to a tree. then that tree is going to point to another tree, and that tree is going to point to a blob. So a multiple layer nested tree is what is going to be returned to us. And that's why above this root entries, I'm going to create a function called create tree recursively, or recursive should be fine. And then I pass in the entries dictionary. It's going to be a dictionary. Cool. And this entries dictionary is actually root entries, all right? But I'm calling it entries dictionary because, well, this function is going to be called recursively. So this function is going to call this function. You'll see how. But that's why it's called entries dictionary. The base case is going to be this root entries. So here what we're going to have is return create tree recursive, and we're going to pass in the root entries. That's going to be the base case, or let's just say the base example or the base parameter that we're going to have. Now, how is this create tree recursive going to work? And what is its function? Well, we are going to recursively create tree objects for this nested directories. So it will traverse the entire dictionary structure and create the tree objects for each level, building from the bottom up. So first things first, let's have a tree, which is equal to this tree. Now we need to add files and create a tree out of it, correct? Now, obviously we need to loop over every single item of this entries dictionary. So we are going to have for name, comma, blob hash in the entries dictionary dot items. And we already know what entries dictionary looks like. It's over here. So we get the name and the blob hash. Then we check if is instance the blob hash of string. Then what we're going to do is tree dot add entry, and then we're going to add 100,644 comma name comma blob hash. Remember this add entry function that we had created? I said that we're going to pass in the mode, the name, and the object hash. And actually we don't need to pass in a tuple. We can directly pass in the mode, which is this. It's a regular file if it's an instance of a string. So in this case, main.py has a value of string, correct? It's the blob hash is a string. So that way we have added an entry to this tree. And remember, this tree is empty initially. So let me draw it out. We have a tree structure wherein, let's just say this is a tree, it has multiple entries, correct? But we have initialized these entries to take in nothing. So entries is none. That means it's an empty list. So that means everything is just empty. And after that, what we have done is go over every single one of this entry dictionary. So we have main.py. Now we have the blob hash, which is of the type of string. That means it's a regular file. So we have added an entry of 100,644, which is a regular file. Then we pass in the name and the blob hash. But if it is not an instance, then it has to be of the instance of dictionary, correct? So we have dictionary here. Then what I want to do is get the subtree hash. Now, how do I get the subtree hash? Well, to get the subtree hash, it's going to be very simple. We just call the create tree recursive, and then we pass in the subdirectory. The subdirectory in our case is going to be the blob hash. Essentially, main.py works out, but when we go to test, it is of the type of dictionary. So what it does is that it calls the create tree recursive. So it again goes through this entire thing. And then it does it for test2, because test2 again is a dictionary. Then it does it for test3, test4, test5. And then finally, when we come to hi.txt, we get this tree.add entry, this particular thing. And then also what we are doing is returning the tree or self.store object tree. So every tree that we create is going to be stored, correct? So towards the end, after every recursion is done, we have like a complete tree mapped out and we return the hashed version of it. Also, once we get this subtree hash, what we want to do is tree.add entry, and then we add 400,000 here, which is a directory. Then we pass in the name and the subtree hash. So this is how the entire thing is going to work. So this should work out, but there's one problem. Whenever I've said 400,000, that's not the case. It's 40,000. I misread it. So yeah, well, let's take an example. So let's go over this one by one. So what we're doing is creating a tree. So this tree is empty as of now. Cool. After that, what we're doing is that for the name and blob hash and entries dictionary.item, so we have this and this. So we are looping over each one of them. We have main.py test, and well, then we recursively keep going inside. But essentially we have two items here, main.py and test. If we have main.py, what we are doing is this thing. If is instance blob hash of the type of string. Blob hash means value over here, not exactly blob hash, okay? It's technically a value. And this value can either be a blob hash or, an object, which is another tree. Or you can say it's another directory, possibly. But for now, let's just call it blob hash. If the blob hash is of the type of string, then we add the entry directly. So our entries list was empty initially. Now we are saying that this list has one contender or one participant. And that is this thing, 100, 644. Then we have the blob hash and another thing, the name or whatever. So that's one element. What we are more interested in is this thing, because that's the tricky one. The blob hash is not of the type of dictionary, so we go to the next one. Now, when we go to the test one, we have a dictionary. So that's true. So we do subtree hash is equal to create tree recursive and pass in the value. So the value here was this particular thing, correct? Let me just remove it. So now we only have hi.txt and all of these things. Now what we see is that hi.txt does have a blob hash of the type of string. So we have another entry here created, which is of the type of 100, 644. So the first iteration is over. Now we go to the second iteration. In the second iteration, we know that the value is a dictionary. That means this test value has this particular thing, right? So it takes this entire dictionary and processes it. So let me just clear stuff out. After that, we are again in the function, because it's called it recursively, correct? So now since we are in this function, we create a new tree object. So here we are now pointing towards a new tree object. Now for name, blob hash and entries deck.items, we have hi.txt, the first value. Well, in the first iteration of the new function call, the hi.txt value is a string. So that means this tree correctly points towards 100, 644. Then we have a name and then the blob hash. Okay, that's done. Now again, we go to the second iteration. In the second iteration, we have test2, this particular thing. The value here is a dictionary. The dictionary. So we again call create tree recursive. So that means this points to another tree as well. And now this keeps going on and on and on for test 3, test 4 and test 5. So once we have all of those trees figured out as well, we're finally on the last one, which is hi.txt, and we have an empty string. Or let's just say we have a value of some sort of string. So that time we again have 100, 644 thing. So with this, the subtree hash is also created. But now remember, we have a stack call. We have been doing recursion. Rest of the function needs to be completed. So this create tree recursive call was called, correct? But the next line still need to be executed. So now once this 100, 644 and name of hi.txt is done, so that means this particular part is also completed. What we do after that is that we kind of start to back propagate in a way, like we have a stack call. We had all of these calls, correct? Now we are going over each of those calls now. So now we are at this particular tree object. Here we say that in the tree, we are adding an entry of 400,000. So 400,000 is created, and then the name and the tree hash is given. And then the same thing happens for this one, this one, this one, and well, this one. And essentially the entire thing fills up. So we work up way from the bottom to the up. So we have a tree that looks like this. Now we take this entire tree towards the end and just store it as an object. So I hope that was understandable. If not, well, this is kind of a logical lead code type question. If you spend more time by yourself or ask ChatGPT or someone to help you understand it, that would be great as well. But yeah, this is what we have done. This was quite tricky to understand, but I think this is the only thing that's the most difficult to understand in this tutorial. So if you did understand it, good job. I admit it's pretty complex. So once we have the create tree index or the tree hash with us, and this is the final tree hash by the way, what we do is, well, use that tree hash to create a commit. Now the thing about commit is commit also has some sort of structure. Commit is going to contain the tree hash. So it's going to contain details about the tree, but it's also going to contain metadata about the commit itself. It's going to know what the current branch is. So what branch was this commit created on? What is the parent commit of this commit? Like what commit preceded this commit? What are the hashes of the parent associated with this? Then we also need to give author information, message, etc. And once all of that is done, we take that commit. We also store that object. So earlier we had done the store object part of this create tree. So as of now, the .get/objects will contain a new object containing the tree. That's what happened in our real Git example. We have ls objects. We have 24, 27, and 94. Earlier there was only one. So a tree was created in one of these hashes. So that's what we have done. And after that, we create a commit and then we also store it in Git objects. So that's great. There's also some other things that we have to do, but I'll talk about them later on. But first, let's just get started with creating the commit object. So first thing that we're going to do is just go ahead and create a commit class. We've created a tree, we've created a blob. Now it's time to create the last one, which is the commit. And after that, we'll have all the building blocks with us. So let's go ahead and create an init function. Here, we're not going to get an object type again. We're going to get a lot of information that we're going to again serialize and convert it into a content format, just like we did with tree. In tree, we had all of these list of tuples, which were entries. So all of the file paths as such, like the file name, the mode, etc. that we created in a tree format. And we converted all of that into content. The same thing we're going to do with commit, but this time we have more information than ever before. The first one that we have is a tree hash. So the tree that we created, it's hash. So this points to the root tree of this commit. Like the entire tree hash essentially that we created. I don't think there's much to explain here. After that, we have parent hashes. Parent hashes refers to all of the previous commits that are present. And the reason it's a list of string is because you can have multiple commits as the previous commits. How? So let's say the user was working on A, B, C. So this is like the usual flow. So this is the main branch, for example. After that, they check out B and start working on another feature, which is D and E. So this is the feature branch. So after this, what you do is check out main. So you're now in the main branch and merge the feature with the main branch. So in that case, what you get is A, B, which is now having D as well, then C, which is the main branch, and then the D is pointing towards E, which is pointing to the main. So with this, the commit M, which is the merge commit that's created, has two previous commits. There's C and there's E. So there is a possibility of having two previous commits. Now, obviously, we're not supporting the merge feature in our git clone as of now, but that's an important consideration to have. We can have previous commits. So it's a list of string. After that, we have author information. In our case, obviously, we don't have author. Then there's committer, who committed the code. Now, these both can be different. The author of the code, so who wrote the code, can be different from who committed the code. So we have access to both. Then there's a message, which is a string. And then we have a timestamp, which is an integer, but if it's not mentioned, it's going to be null. And this means that like when the commit was made, and this is like the information about the commit message. Cool. Now we can pass in the commit here. And then we need to create a content. For that, we have to serialize it. But first, we'll have to initialize each and every one of them. So we have tree hash is equal to the tree hash. Then we have parent hashes is equal to the parent hashes. Then we have the author, which is equal to the author, followed by the committer, which is equal to the committer. And then finally, we have message and timestamp. So yeah. And if the timestamp, by the way, is not mentioned, it's going to be null. And if it's null, we are just going to do time.time. Time.time means what's the current time. After that, we need to serialize the commit. So for that, we're going to have def serialize commit. And this is going to be rather simple, so no need to worry too much about this. The commit is serialized in the format of like tree. Then you pass in the tree hash, then you have parent, then you have parent hash passed in, then you have author, then you pass in the author's name, the timestamp, then the time zone. So this is how, like literally how the commit is serialized. It's not like tree where you need to pass in structure like this. So you have passed in mode, name, \0, nothing like that. What you have instead is a simple line by line list. So you have lines is equal to, and then you pass in a list where you pass in tree, and then you have self.tree hash. Okay. Also we have self over here. After that, what you do is for every parent hash in this parent hashes list, what you do is lines.append, then you pass in the parent and parent. Also, this is going to be self.parent hashes. So for all the commits, we have said that this is the parent commit. After that, we add lines.append, author, self.author. Then I told you that we need to specify the timestamp, and then we also need to specify the time zone. The time zone is essentially like how much away are you from UTC. If you don't know what UTC means, you can just search it up, UTC time zone, which is the Coordinated Universal Time. It is the primary time standard globally used to regulate clocks and times. If you're from India, you are plus 530 UTC. But in our case, we don't need to worry much. It's going to be plus 4 zeros. Why is it plus this 000? That's because this time.time that we have is always going to be in UTC because it returns the current time in seconds since the epoch. And if you search about it, it will say that the number of seconds that have passed since the Unix epoch, which is January 1, 1970, this is 000 UTC. So this value is always in UTC. That's why we have done this. Cool. After that, we need to do the same thing, but for the committer. So we have committer like this, committer. Then we have lines.append, an empty string, and then lines.append, and then we pass in the self.message. Now you might be wondering, why do we have a list here? We have a list because what we are going to do is return \n.join the lines. Now, why have we created a list when ultimately what we wanted to do is concatenate each one of them by a new line? The reason we did this is because of saving time complexity. If you add two strings together, it's O of n square, kind of. But when you append to a list and do this, it's O of n. So we are saving time when we do this. And that's why I've done lines.append of an empty string. That's because we'll have something like this. So we have a tree like this in the first list, followed by parent in the second one. Then we have this thing in the third one, and so on. And finally, we have this thing, correct? So an empty string. So what you do is /n.join lines. So you take this, you have one line, then you put in \n, then you put the next line, then you have an empty string, then you put \n again. So you're on a new line every single time, and that's great. So this is how we have serialized the commit. Now what we want to do is create a content out of this. So we have content is equal to self.serialize commit. And now we can pass that content in. That's great. We now have a commit class. Now, obviously, since we have serialized it, we also want a deserialized thing. It's again going to be class method. After that, we're going to have from content, we're going to get a class. Then we're going to get the content in bytes, and we're going to return a commit class after this. Now, I think this should be quite straightforward for you as well to understand. So we are going to have lines is equal to content.decode because, we have a bytes format here. And actually, I've missed out on doing one thing. I do tell you that this is in bytes format, but I've not converted this to bytes, correct? The serialized commit, we have all of these things, but then we are returning a string. We don't want to return a string. We want to return a bytes thing. So we encode all of this string into a bytes format. So make sure you do that. Cool. So from here, we get the content, which we decode. So now we have a string, and on this string, I'm doing a split by /n. So yeah, I'm going really fast over here because I don't want to spend much time on things we've already learned. We're just deserializing this. So a reverse of this function. We are decoding the bytes that we get. Then we are splitting by n because we joined it by n earlier. And now we'll extract each one of this information. So we have tree hash, which is going to be none. Then we have parent hashes, which is going to be an empty list. Then we have author, which is equal to none, committer, which is equal to none, and then the message start index, which is equal to 0. Okay, so like, where does the message start? What index does it start at? Now what I'm going to do is go over every line that's present and try to extract the information out of it. So now what I'll do is for I comma line in enumerate the lines. What enumerate does is that it gives me the line. So each line that's present in the list, because we have splitted it by n, \n, right? We do if line dot starts with, and we start with the tree. That means we have a tree hash with us. So that is going to equal to line at 5 till the end of the line. Why is it 5? Because see, we have t, which is 1, 2, 3, 4, 5. So we have to skip the 5 characters and go till the end of the line. So we are ignoring this thing and we are grabbing the entire hash that's present. And we're going to do the same thing for everything else. If the line dot starts with, let's say, parent, then we are going to do parent hashes is equal to, and actually we can't do is equal to over here. If we do parent hashes is equal to line at, let's say, 7 colon, because parent is 3, 6, and then the 7. So we can't do that. Why can't we do it? Because remember, we have multiple parent hashes. If you do parent hashes is equal to line 7 at, it will grab a string, but then the next time it again sees a parent, it will override that value. We don't want to override. We want to get and append to this parent hashes list. So what we are going to do is instead append this with line 7 till end. After that, we are going to check if it starts with author. Then we have to extract data from that author line, because in author, we have the author name, we have the timestamp, and then we have the time zone. We need to extract all of them, correct? So here what I'm going to do is have author underscore parts, which is equal to line 7 till the end dot rsplit. Rsplit returns a list of words in the string using sep as the delimiter string. So I'm just going to split by a space, and I'm only going to get 2 results from here. Then we have author is equal to author parts at 0. So we take the first thing, that is going to be our first author name. And then we are going to have timestamp, which is equal to int author parts until, and that's going to be 1. I said that the max split that I can have is 2, right? So we only have 2 elements in the list. So the first one is going to be the author. So it's going to be this thing. And then we have this thing as the second one, which is self.timestamp plus 0000. All of that is used in int to convert to a timestamp. After that, we have elif line.starts with committer. And for committer, it's going to be the same issue. Make sure you pass in spaces, by the way. And yeah, as I said, it's going to be the same thing. But in committer, we probably don't care about the timestamp as much. All we care about is committer parts. Then we have line 10, not 7, because committer is a longer word. We have 4, 7, 9, 10. So yeah. And then we just take the committer is equal to the committer parts at 0. And finally, we just check if the line is equal to an empty string. Well, that means our entire thing is coming to a halt. That means we have done the tree, parent, author, and committer parsing. That means on the next line, our message is going to start, correct? So we're just going to have message start is equal to I plus 1. Because on the next line, our message is going to start, and then we can break out of this entire loop. We don't want to execute any further. After this, I can get out of the for loop and say that the message is equal to \n dot join, and we're going to join the lines from message start till the end. Cool. So what I've done is that I've parsed all of this data. Once I get to the message, I'm joining all of the lines from message start, which can be the last line or it can have more lines, who knows, till the end, and I'm joining everything by \n. So that's going to be our message. Then we can create a commit, which is going to be a class, and we have to pass in all of these details. So the very first thing is tree hash. Then the next thing is going to be parent hashes. Then the next thing is going to be author, then the committer, and then the message itself. I think that's how it goes. Triage. Oh yeah, and we also have timestamp, I think. So yeah, timestamp. And remember, the timestamp that we have put in is for the author. We have not done it for the committer, because if we put timestamp is equal to the committer over here, the value will be overridden. I don't think that would be a problem though, because I think we're using the same timestamp. So yeah, should be fine. But yeah, this way we are done. Let's return the commit object from here, and we're so ready. So we have created our own commit class. Now we can use this class instance in the commit function, but we do need other information, correct? To create a commit object, we'll need all of the parent hashes. The tree hash is already there with us. Then we need the parent commit, and we have to figure all of that out. But first, let me just go ahead and create the commit object like this. Let's input everything we have. Tree hash, that's present with us. So we can pass in the tree hash. Now the things that are left are parent hashes. So we have to figure that one out. Then we have author. Well, we'll have to put some value that's present over here. Cool. Then we have committer. In our case, the committer is the author. We are not going for complex use cases, but if you want, go ahead, read about it and implement it on your own. That's the recommended way anyways. Then we have message, which is equal to the message. And then for the timestamp, we're going to keep it null so that, it takes the time.time. It automatically gets that time, and that's cool. Now we only need to create a parent hash. And to remind you, parent hash is essentially the parent commits hash, and there can be multiple parent commits. So you have hashes of all of the direct previous commits to this particular new commit. So let's say we have these as commits. So this had a message of hi, this had a commit message of hello. Now we are adding a new one. Okay. Now, since we are adding a new commit, we need to get access to the previous commit. And this previous commit is only known by its hash. That's how we have created our entire Git clone. Everything is recognizable by a hash, and even a commit has a hash because commit, if you go at the top, extends Git object, and Git object has access to hash. So the same thing is going to happen here. What we need to do essentially is that in the branch that we are in, there can be multiple branches as well. Remember that. So in this current branch, let's say we are on the main branch. For this branch, we want to get the latest commit. And this latest commit is going to be our parent commit. Now we want to get this parent commit's hash. Once we get this parent commit's hash, we assign it to the new commit that we are going to add. So this is kind of like the commit history that we have created. So just with this example, we have understood a very essential thing that first we will have to get the branch that we are on. Now by default, we are on the main branch, but we can be on some other branch as well. The true value, as we know, is given in this head file. So we need to extract data from this head file to know what branch we are currently on. We are going to support the method of git checkout. So we can go and play around with some other branches as well. Like for example, we can create a feature branch or we can create a main branch. So that's where we are going to edit the head file. We have other files to edit as well, but this head file is going to be the source of truth for what branch we are on. So we simply have to read this file, get the branch. Once we have the branch, so what branch the user is on, we need to get that branch's commit. And once we get that branch's commit, we just need to hash it and then return it to the user. In between, there are some edge cases, but we'll figure that out. So let's get started. So let's go ahead and create a function that will allow us to get the current branch. So here I'm just going to create a function called get underscore current underscore branch. And well, it's just going to return a string here. And what does this function do? Well, as I said, we just need to read the head file. Now, do we have the head file? Yes, we've created a head file at if not self.head file. If you remember, this is how we had initialized it, get directory /head. That's how we created it in the first place. So if not self.head file exists, so if it does not exist, in that case, we are going to default it to a master branch. Now, if that does not exist, or I mean, if that does exist, in that case, what we want to do is get the head content. So we have self.head file.read text. Or not read bytes, read text, because we are storing it in a text format, correct? And then we're also going to strip off all the spaces that might be present. And I don't think it would be, we're not writing it, but just in case. After that, we can just do if head content dot starts with, and if it starts with ref colon, and let me just put in ref colon within a double quotes. And then if it starts with refs heads, like this, that means it is the file that we were looking after. So we'll just do return head content from 16. That's because this is 3, 4, 5, and then this is 9, 10, 15, 16. So we need to skip all of this and we'll directly get the branch. Now, if it does not start with ref heads or whatever, again, we're just going to return a head from here. We are not returning master, we are returning head. Why? This is the detached head. What does that mean? Well, that means that the head that we have, like this head file, this does not directly point to a branch as such. It points to a commit, and that can happen. You can directly point to a commit by checking out to a commit. That's totally possible. So just in case that's the issue or that's the scenario, we'll just return head, which is the detached head. But most of the times we are just going to follow this condition. Cool. Now, after we get the current branch, what we need to do is get the commit related to that branch. First, we'll go ahead and create a current branch is equal to self.getCurrentBranch. So now we have access to the current branch, but now we need to get the commit associated with this branch. So think about it. Okay, we have this entire commit space, correct? Just think of each node over here as a commit. Now all of these commits are present within a branch, correct? Now how do we know what's the latest commit in this branch? It needs to be stored somewhere correctly, and yeah, it is stored. If you go to refs/heads, I told you that in this particular path, we will have branches pointed out. So we'll have a master branch, and this master branch will have some commit written out. Then if there's a main branch, there will be some commit written out over here. So there will be a master file, like just a file called master, within which there's a commit hash present. So there will be a file where a commit hash is present. The same goes for main or any other branch you create. So in this refs, we have heads, and within this we'll have the thing. But what if we don't have the commit? And by the way, that will reflect the latest commit, all right? Just to be very clear, it will be the latest commit. But right now, if you see, we don't really have any commit, correct? So it's empty. In that case, what do we do? If that's the case, then we'll just return an empty parent hashes, because this is the very first commit. We don't have anything else. So it will be an empty list. So we'll handle that case. So now what we're going to do is also create a new function, and that function will be get branch commit. Then we'll have self, and then we'll take in the current branch. Okay. So this is going to be the branch for which we want the commit. And now, as I said, the commits are stored in refs heads. So we'll go to this heads file. So we have self.head file, not head file, head directory, sorry, because this is refs heads and this is a directory. It's not a file. And within this head directory, we are going to have a file of master or main. And in that master or main file, we'll have a hash written out. To give you an example in real life Git, I'm just going to ls it. So we have our refs here. So cd into refs heads and then ls it. So we have a main file over here, because by default, the new Git creates a main branch, correct? So there's a main thing over here. And if I cat the main thing, we have a commit written over here. That's the only thing that's present in this file. We're going to have a similar thing. So we have the heads directory, and we concatenate that with the branch or the current branch. And all of this is stored within the branch file. So we have branch file like this. After that, we check if branch file dot exists. If it does exist, then what we want to do is return the branch file after reading it, correct? So we have return branch file dot read text dot strip. So we just remove all the white spaces from the front and the back. And if it does not exist, then we return null. That's as simple as it gets. We just read the file, get the commit hash, and then return it. So let me go back to the commit function, and here I'm going to have a parent commit is equal to self.get branch commit. Cool, and I'll pass in the current branch here. After that, I'm going to have the parent hashes, which is equal to the parent commit, and it's only true if the parent commit is present, otherwise it's going to be an empty list. So as I said, what if in this particular scenario, we don't have any previous commit? We didn't have it, so we return null from here. The get branch commit returns either null or a string. So in our case, it will return a null. So parent commit is null here. And then what we do is create a list with parent commit within it if the parent commit is not null. And if it is null, then we are just going to have an empty list. Okay. Once we have the parent hashes, we can just store it over here. But there's some additional checks we would like to do. First of all, we would like to check if there are actual changes to commit. For example, let's say the user has the file hi.txt only. Okay, so this was in the working directory. Then the user does git add and add it to the staging area. So now you have hi.txt in the staging area. After that, git commit is done and then it's added to the local repository. All right. But now let's say the user again does not modify the hi.txt and again does git add and then again does git commit. It will again register this commit, correct? Because in our current logic, we are not checking if the file has actually changed or not. And that's why we need to check it first. How do we check it? Well, I told you, if you remember, that as soon as we commit something, we are going to clear off the index, right? The real Git handles it with more complexity. In our simple scenario, we are going to wipe off the entire staging area. So the staging area no longer has hi.txt, it's empty. So let's get started with that. And then we can add a logic to check if the index is null. If the index is null or it's empty, then there are no files in the staging area. And then we can also add another logic, and I'll talk about that shortly. But first, let me just go ahead and do self.store object, and we store the commit object to our .get/objects database or data store. And this will give us a commit hash. After that, we are just going to wipe off our index. So we have self.saveindex where we just empty out the entire file. Then we say print if created commit, and then we pass in the commit hash here. So this is the commit we created on the branch, and the branch is the current branch. Okay, that sounds good as well. And then finally, we can return the commit hash from here. Don't think there's much use of it because even over here, we are not doing anything, but yeah, who cares? We'll just return it. Just in case you want to add unit tests, this is a good thing to do, to return the commit hash. Okay, now what I would like to do is just check the index, that if it's empty. If the index is empty, that means there's no changes to commit, because the last time we committed, we cleared off the entire index. So what we're going to do is if not index, that means the index is empty. And first I need to load up the index now. So index is equal to self.load index. And if the index is empty, in that case, we will just print out nothing to commit, working tree clean. And then we'll return none. So this logic will get triggered when, let's say, the hi.txt has been committed. So we have a node here which has been committed. Now the user tries to commit again without adding this hi.txt. That's the point where this condition will get triggered, because staging area is now an empty dictionary. Nothing is present in this. But there's another edge case that we'll have to notice. And that is, we also need to compare the hashes of the commit object that has been newly created. So this particular tree hash and the parent commits tree hash. We have to compare both of these tree hashes. And if they are equal, that means there's nothing to commit because no changes have really been made, correct? So what I'm talking about is, let's say hi.txt has been committed correctly. Now let's say the user adds hi.txt again. Now if they try to commit it, that should not work. Why? That's because hi.txt has not been modified. So that means the content that's present in this commit and the content that will be present in the new commit will be the same. If they are the same, why are we allowing it to commit? There are no real changes, not even one character. And that's why we are going to compare their tree hashes. Because if you remember, tree hashes were created based on the directory structure and the content that's present within them. It's like a bundle up of the entire staging area. So we'll just compare their tree hashes to ensure that they're not the same. If they are the same, we'll just say nothing to commit. Your working tree is clean. Don't worry about it. So how do we do that? Well, first of all, we check if the parent commit is even present. If the parent commit is not null, so this thing does return an actual parent commit. So one thing is present. Then what we're going to do is load up the commit object. So here the commit that we are getting is a hash, correct? It's like a parent commit hash. It's a string value. What we need to load up is the actual object, the actual parent commit object. So we load that up. So we do self.load object, and now we need to create a function to load up that object where we pass in the parent commit and it just loads the object as it is. So let's go ahead and create it. I'll create it somewhere roughly over here because, well, it might be a reusable function because we take in an object hash. So that means it will work with any get object and it returns a get object. After that, what we do is, well, you know what we want to do. We go to the particular get object. So we go to this pyget objects. We go to this directory. We go to this particular hash. Like, let's say this was the hash that was mentioned. We go to this particular hash and see if the file is present. If the file is present, then we are going to deserialize it and then we are going to return it. And if it's not present, we are going to raise an error. So here we're going to do object directory is equal to self.objects directory concatenated with object hash. And this goes from 0 to 2, the first 2 characters. Just the reverse process, or like the process that we have already done. Then we get the object file, which is object directory / object hash, and then we go from 2 till the end. Cool. After that, we'll just check if not object file dot exists. If this does not exist, we'll return file not found error. If object with this object hash not found. And well, if we do find it, then we're just going to do return get object dot deserialize, and then we'll pass in the object file dot read bytes. So to give you a larger perspective of what we are doing, we are calculating the file path from the hash, we are reading the compressed bytes, and then we are deserializing it into the appropriate object type. So get object dot deserialize will construct the get object, whether it is a blob, tree, or a commit. Cool. Now I can take this load object, call it over here, and now we have a parent commit object. But just having the parent commit object is not enough because we need the parent commit data as well. So this is more like a get object, correct? This contains the content as a whole. We don't want content as a whole. So just to go back to this deserialize function, this is returning the content, correct? But if you remember, our commit looks very different. The commit has all of these properties. We want these individual properties so that we can access the tree hash. So essentially, we want to call the from content method of this commit to get the actual data, to get the actual commit object. The previous one was a generalized get object. It was containing the content. So it contains like a data that is made up of all of these things. Now we want to extract those particular things. And that's why we are going to call commit.fromContent. So what we're going to do here is after we get the commit object, or let me just call this parent get object, and we know it's a get commit object and it should be $M. And after that, what we can do is parent commit data, which is equal to commit dot from content, and then we'll pass in the parent get commit object. If we just pass in this much, it's not enough because parent get commit object is of the type of get object. But what we need to pass in here is bytes. So what we are going to do is dot content. We know content is bytes, and content is made up of all of the things that we want. So once we pass that in, it will give us the commit object that we require. And now finally we have access to the tree hash. Now I can use the tree hash. So I'll just do if tree hash, and this tree hash is coming from this one, create tree from index. So for the new commit that we are going to add, we have a tree hash, And then we are going to check if it's equal to the parent commit data dot tree hash. And if that is the case, we are going to print nothing to commit, working tree clean. And then we'll return none from this. Remember, even over here we return null. Even here we return null because we don't want to execute any further. And if that is not the case, if all of this is like false, we just commit everything, save the index, and yeah, we will be done. But there's another thing we have to do. Remember, I said earlier that refs heads main will contain the commit, the latest commit. So we also need to write to this particular file to update the commit, right? So what we have to do is create a function to set the branch commit. We had a function that got the branch commit. Now we set the branch commit. So we'll have a function set branch commit. Then we'll have branch file is equal to self.heads directory / current branch. That's correct. And after that, we won't check any of this. We don't care if it exists or not. What we are going to do is branch file dot write text, and then I'll pass in the commit hash, which we are going to take from the parameter. So we have commit hash, which is of the type of string, and then we just pass it in, followed by \n. Now I can take this set branch commit and add it somewhere over here. So I don't think the order matters that much. Just make sure you do it before save index or after save index. I don't think it would matter that much, but self.set branch commit, then I pass in the current branch I'm on, then I pass in the commit hash, and we're done. So now the branch commit will be updated. So in refs heads, we'll have a new file called main or master, and it will contain the newest commit. Every single time the newest commit will be updated over there. And with this, the entire commit should work as expected. So what I'm going to do is, well, open up everything, make sure index is just that. None of my edits exist. Now I'll do Python 3 main.py commit -m. Hey, is this working? Hit enter, and it says init missing one required positional argument entries. This error exists because I searched for whenever the tree was called. I knew I need to search for tree because init missed one required positional argument. This will only occur when I call the tree object, right? Like I create an instance of tree. So I searched for that and I noticed that tree is called like this. So it should be empty, that's correct. But here I'm saying that entries should always be present. And I'll edit that by saying that, hey, if you don't specify, it's going to be null by default. Okay. And now I can say that entries, if it's present, will be used here, otherwise an empty list. Now let's try this again. And we say created commit this on branch master. Now I'll open this up and we have two new things. We have 25 with this, and then we have 6b with this. So we have a tree and a commit similar to the real Git that's been created. Now if I go to refs heads, we have a new file called master, and now we have this thing showing up. Now if you notice, the 6bb6620 is the commit, 6bb66. So that's the commit hash that's been stored in master. And that's true for the real Git as well. So we saw that this is the hash that's present in main. Now if I go out of this refs folder and go into the objects folder, ls over here, and we have 94. So that is the hash present. Now if I cd into 94, ls it, we get df0905. So essentially the same thing. That's how the entire process works. And if you've understood this, feel free to skip to the next part. But now what I'm going to do is recap the entire commit process now that we have all of the code required. So let's start with the main function. What we are doing is having a commit parser. Here the commit parser takes in a message and an author. After that, if the user specifies the message, we call the repo.init command or repo.commit command, sorry. Now here we first create a tree hash. So we create a tree object from the index. The index is the staging area. The staging area, by the way, is now empty because we have cleared everything off. Once a successful commit is done, the index is empty. Then we create a tree from the index. Now this was the most difficult part, and I think I've explained it 2 to 3 times already, but I'll just give a brief overview so that I don't waste much time on this or spend much more time on this. So I load up the index from the particular file. So this file. After that, I check if not index, we are going to create a new tree and then we are going to store it. So if the index right now, for example, is empty, correct? So it will just check that, hey, if it's empty, I'm just going to create an empty tree. Cool. Now we have directories and files. We noticed that this entire thing that we have, all it does is put all of the files that are present in the root of the folder, for example, the main.py, that will be stored in files, and all of the directory related stuff will be stored in this object. That's exactly what this logic is doing here. After that, we have done root entries is equal to the files. These 3 lines are essentially concatenating the entire files and the directory dictionaries so that we have one particular dictionary. After that, we call the recursive function of create tree recursive. We pass in the root entries. So we have main.py, we have like this test folder, everything passed to it. After that, we create a tree recursively. So we have a tree which is empty. For name blob hash, this blob hash is in reality a value. If this value is a string, that means we have a blob hash. If it's a dictionary, that means, we have a nested dictionary structure. So what we need to do is create a tree. So we call this function again and create this entire tree. And every time we encounter a directory, we create a tree. And well, finally, after everything is done, let's say we reach the hello.txt file in this test2, we will kind of continue from hello.txt and go back to test2 to test. So what we do is that we add the entry of 100,644 for hello.txt. Then this entire function gets over. So what we do is we return self.store object. Then we go to the test2 folder and we have done this. Now we have a subtree hash for this because, we returned self.store object here. So hello.txt returns something that is given to test2. We add the entry, then this function gets over. Then we go to test and test also executes this. So we have the folders and the files properly created. So this is how we create the tree from index, the most complex part of this app or the program. Once we have the tree hash, we add it to the commit object. Now we need to get the parent commit. Now, how do I get the parent commit? Well, for that, I need to go to this particular file called refs heads master. And here we have a parent commit. So we can take this commit and add it to the parent hashes. Parent hashes was a list because we can have multiple commits, but we are not adding support for them. If you want to go ahead and try it out on your own, please do so. There's so much scope to improve everything, and that's such a good learning opportunity. So feel free to do that. So anyways, we have the parent hashes here. If the parent commit is present, then we load up the index. If the index is empty, we have not added anything. It will say nothing to commit, working tree clean. Let me try that out. We have not tested that out. So I say, hey, this is working, and it says nothing to commit, working tree clean. Then we check if the parent commit and the new commits tree hashes match or not, because tree hash is like the ultimate source of truth of whether the content is same or not, because if they have the same directory structure, if they have the same files, and each file has the same content, because we are storing everything in this tree, correct? Because if we go back to the create tree from index, we are storing the blob hash as well. We are adding the entry over here for the blob hash. So if all of that is true, That means we have nothing to commit working tree clean. And I'm going to try that out right now. So what I'm going to do is add the main.py, and actually I think the main.py has changed now. So we are not going to get the same thing, but yeah, we get an error, a bytes like object is required, not string. Now this error exists because if we scroll up to get object and call the deserialize function, here we have done header is equal to decompressed from 0 to null index, correct? But what we've forgotten to do is dot decode. So we need to call dot decode on this because this is in a bytes format, correct? Everything here is in bytes format. So we go till here and we decode it so that we get actual English so that we can split it apart. The content is not decoded. The reason for that is the content shouldn't be in bytes. That's what this get object also requires. But the header, we need to split it apart because we need to actually understand it to get the object type and the size, correct? So let's save it. And now I can do, hey, is this working too? And it creates a commit. Well, it does work out, but let's say if I again do add main.py, the file has changed. So again, a commit should be made. So yeah, it should work. But after this, it should not work because now the tree hash of the latest commit and the new commit that I'm going to make should be different. The previous two did not work, just to be very explicit, is because I changed the main.py file. But now I've not changed anything. So let's see. And it says nothing to commit, working tree clean. So that means the tree hash comparison is also working great. So this logic is also seen. Now what we do is just store the object in git/objects. Then we set the branch commit to be latest. So that can be seen over here. Then we make sure the index is again empty. We print out the message and return the commit hash. So yeah, that's pretty much everything about commit. Now the next operation that we want to support is checkout. Checkout has multiple things. You can switch to another branch, but you can also support the creation of another branch. So if you do git checkout -b, let's say new branch, that means you're creating a new branch. But if you just do git checkout new branch, it might give you an error because the new branch does not exist yet. So if you do -b, you can create one. And if you already have one, you can move to one using this. So that's the only thing we need to be concerned about, but rest everything, we just have to edit this head file. So let's add support for it very quickly. So here we are going to have a checkout command. Then we are going to have a checkout parser, which is equal to subparsers.add parser. Then we add in checkout here. The help message is going to be to move or create a new branch. After that, or we can just call it manage branch, I guess, but that's also fine. Now we can just do checkout parser dot add argument, and then we add the support for -b, correct? Because if you want to create a new branch, you can do that. And I'll also like to be explicit by doing -- create branch. Then we have an action of store true. That means if the user specifies -- create branch, it is automatically set to a Boolean value. So this gives us like a Boolean value. So if we check if args.b is present or args.create branch is present, like we can just see if it's a true or false value. That's what action does. Then we can have a help, which is create and switch to a new branch. Also, we are going to have another argument here, which is going to be checkout parser.add argument, and then we have branch here. The help is going to be branch to switch to. And well, obviously this means like if you do git checkout new branch, so new branch will be stored in this branch. Okay. So let me go ahead and add an elif condition here, which is elif args.command is equal to checkout. Then what we are going to do is this thing. If not repository.getDirectory.exist, we print this out. Otherwise, we just do repository.checkout and we pass in the args.branch. So that means this is the branch name that we are checking out to. And then we have args.create branch. Args.create branch is like a true or false value. Do we want to create a branch or do we not want to create a branch? So here we are going to have a function of checkout. So we have a self branch, which is a string. So what branch are we going to? And then finally create branch, which is going to be a Boolean value. Do we want to create a branch or do we not want to create a branch? Finally, we are going to go ahead and finally just get done with it. So we have self.heads directory /branch. We already know this procedure because we have done the same thing in commit, but essentially refs heads here, we are going and adding a new branch. And then we're just saying if create branch is present, then what do we want to do? Otherwise, what do we want to do? Well, even before this if condition, we'll have to put another if condition, which is if not branch file dot exists. So what if this branch file does not exist in the first place? If it does not exist, then we want to check if this create branch was specified. That means git checkout -b something was done. If -b was not present, we are not creating a new branch and this something branch does not exist as well. So in that case, we are going to print out branch and we are going to specify branch here, not found. Then we have print use, let's say Python 3 pygit.py checkout -b branch to create and switch to a new branch, and switch is spelled incorrectly. Cool. That sounds good. After that, we are just going to return so that we don't execute anything that's present further. And if create branch is present, then well, we want to create a branch, right? So what we can do is get the current branch, get the current commit, and set that branch's commit as the current commit. Because even if you check the real git and let's say I get out of this .git folder, here if I do git checkout, let's say hello, well, hello did not match any files known to git first of all, but also if I do git checkout -b hello, it switched to a new branch hello. And now if I do git log, which is like all of the commits that have been made, it takes the most recent commit that's present in master, the branch I switched from. It takes only the most recent commit and adds it to this new hello branch. So if I go to cd.git ls and then let's say I go to refs followed by heads and then we have hello here. If I print out the hello file, we have the most recent commit that we made exactly matching here. So what we want to do is get the current branch, get the current commit, and then in the new branch, set that latest commit. Cool. So let's get the current branch and all of the helper functions are already created. So we have get current branch, gets me the current branch. Now I get the current commit, which is equal to self.getBranch commit. Then I pass in the current branch. This is all done in the commit function as well. This particular thing somewhere over here. And then what we do is check, is the current commit even present? It can be null, right? Because nothing has been done. We are directly going to a new branch. That's also possible. No previous commits in the current branch exist. So in that case, we do self.set branch commit. Then we pass in the branch, which is, well, the new branch. And to this new branch, I want to set the current commit. So it's this particular hash that we get. So with this, the data within refs, heads, and the new branch that we have will be updated. Then we can just print out that, hey, we created new branch, and then we pass in the branch here. This is the branch that we've created. Now, if the current commit is not present, what do we do? Well, we just print out no commits yet, cannot create a branch. If you want to support this, like for example, no commits are present, but you still allow the user to switch to a new branch, go ahead, do your thing. After this, what I need to do is update the head to point to the new specified branch. So what I'll do is self.head file.write text. And here I'll update this. So right now it's ref heads master, correct? But I'll remove this master and I'll set it to the new branch that the user has specified. And also I need to put a \n because even over here we leave \n, a new line. After this, we can say print switched to branch. And let me just pass an F here. Now with this, you might think the checkout is done, and you're right to think so, but there's a big bug. And the big bug is that, let's say I do git checkout -b something. Oh well, it's not a git repository, sorry, we did not have to do that. We had to do python 3 main.py/b new branch, and I again forgot to do checkout, sorry. Yeah, we get created new branch, switch to new branch, and we do get this, and we get the latest commit. Okay, that sounds good. Now let's say I go to the head and it points to the new branch. Now let's say I do new branch again, and well, nothing happens. That's also fine. New branch is already created, so why bother? But now let's say I go to master. Why doesn't that update? Well, that's because this head file.write text should not happen within this create branch only. It should happen irrespective of whether the branch file exists or it does not exist. Because it can be that the user is just trying to move from one branch to another. They're not trying to create a branch. So how does it matter if none of these things are present? Correct? So that's one of the bugs. Now, if I try to check out master, we switch to branch master. That's good. I go to head and we are now back at master. Now, if I try to move back to this new branch, I switch to the new branch. And if I try to do new branch 1 not found, use python 3 pygit, that's not my file name, that's main.py. So yeah, looks good. And yeah, so that's one thing. Now the second thing is that when we check out, what exactly happens? So let's say I checked out into the new branch. So I'm now in the new branch. Here I do some add. Okay, so I do python 3 main.py, and let's say I add the newly edited main.py file. Okay, I also commit over here, and let's just name this main.py. Okay, I created the commit on the branch new branch. But now if I move back to the master branch, the issue will be that my working directory will still reflect the latest commit that's present over here in the new branch. So the working directory does not really update. What has updated is like all of the files that are present over here, but the real sync does not happen. To explain this to you, I'm going to do a small demonstration. What I'm going to do is remove all .pygit and replace it with .git, so that the content actually changes in my entire folder. So instead of .pygit, we are now depending on .git, and I have extensions for Git in VS Code that will allow me to see the changes in real time. Let's say I have two branches. I had master branch, I had branch 1. In master branch, I created one commit, and then I checked out to the branch 1. So this commit was carried out in branch 1. And this is just the main.py commit, alright? After that, what I did is created a new commit which contains the branch1.txt. Now I'm going to create another commit of branch 2.txt commit that I have. and I go back to this master branch, what should happen is that these two files should not be visible because they are newly created files. Master is not tracking them. And the reason it doesn't work out is because if you look at our checkout function looks something like this. All we are doing is editing some files, but we're not really making any changes such that it can be reflected on our machine. Even if you change this .pygit to .git, you will not notice the difference because right now we are doing .pygit, so VS Code is not picking up the changes. But also we have not really made any changes to our working directory. So we need to make the changes. What we need to do specifically is that we need to compute the currently tracked files from the previous branch. So this is the previous branch, correct? Let's say we are on master, we are checking out to the new branch. So this was the new branch. For that, we first need to compute the currently tracked files from the previous branch. So that means we have to compute the tracked files from the master branch. Once we find out the tracked files, we can clear them off. And then once we clear off the files from master, we can go ahead and install the branches from the new branch, correct? So step 1 is just clearing out all the files that are tracked in master to be removed from the working directory. How do we do that? Well, let's go ahead and at the top, just create a variable called previous branch, which is equal to self.getCurrentBranch. So this is the same thing as this one, but right now we are calling it previous branch because, well, it is the previous branch. We are checking out, so we are going to the new branch, which will be the current branch. And then we can create a variable called files to clear, which is equal to a set. And then we need to put a try and except block. So let me just do except exception. And if some error occurs, then we can just say files to clear is going to be an empty set. Also, this is a wrong spelling, so let me just fix that. Cool. Now here we need to, well, get the currently tracked files. How do we do that? Well, for that, first we need to get the commit hash, correct? So this is the same code that we're going to use. So we have current commit is equal to self.getBranch commit. And we can also call this previous commit. And to be very specific, we can say previous commit hash. After that, we can just check if this previous commit hash is not null because it can be null. That's exactly what we had done over here. And now what I want to do is load up the commit object. Why? Because I want to get its tree hash. Because what we're going to do is get its tree hash, and from the tree hash, we'll get to know all of the files that are in the specific branch. So understand what I'm doing here. What I'm doing is first getting the branch that we are on. So the master branch, for example, then I'm getting its tree hash essentially. So the tree hash will help me find out all the files and directories that are present within this particular branch. So in master, whatever we have committed till now. And once we get that, we can clear off all of the files. So files to clear will be all of the files that are present within the tree hash. So here, let's go ahead and create previous commit object, which is going to be equal to self.load object. And then I can pass in the object hash, which is previous commit hash. After that, we can go ahead and create a variable called previous commit, which is equal to commit.fromContent. So as of now, we have loaded up the Git object, but Git object has access to content. We want to get the very specifics, right? So that's why we are doing commit.fromContent, which will break it down into the various commit details like tree hash, previous hashes, author, all of that. So we can take that, pass it in, and yeah. Also, we can't pass in the object. Actually, we need to pass in the content here, previous commit object.content. Now I can do if previous commit dot tree hash. If previous commit dot tree hash is present, it's not null, it's not empty, etc. What I want to do is set files to clear is equal to the previous commit dot tree hash, correct? So I have the tree hash now. Files to clear is the tree hash. Is that correct? Not really. What we need to do is load up all the files that are present within this tree hash. So we'll have to kind of decode it. What we had done before is recursively created a tree hash out of all of the files and directories. Now we want to reverse that process. And for that, I'm going to create a function called get previous, or not get previous, let's call it get files from tree recursive. And we can pass in the tree hash here. That looks good. After that, we'll ensure that we use this files to clear and clear stuff up. But as of now, I want to create this function. Let me copy it, and somewhere here I can just create the function def get files from tree recursive, and here I get access to the tree hash, which is going to be a string. Now, how do I get the files from the tree recursively? So let's understand what we want to do here. We want to get all the files that are present within the tree object. So for that, our output is going to be a list of files, or a set of files essentially. After that, what we want to do is try and except block, because there is an exception that can occur here. And if that error occurs, we just want to say that, hey, there's a warning here that I could not read from the tree with the tree hash that's specified here. And if we want, we can also probably pass in the error message and fix the spelling error, explicitly saying that this is the issue. After that, obviously, we want to ensure that we can return files, irrespective of whether there was an exception or not, because if there was an exception, files is going to be an empty set. So we can just return it. The first thing we want to do is load the tree, because if we only have the tree hash, we'll have to load the tree, then we can access the content that's present within the tree. So again, similar to commit, we are just going to have tree object is equal to self.load object. We'll pass in the tree hash, but after that, we'll also have to create a tree. And this is going to be the real tree. Here I'll pass in tree object dot content, and now we have access to the tree itself. If you remember, tree had something like this as the content. It had a list of tuple, and there were three things over here: a string, and a string. So the first one was a mode, the second one was a file path, and the third one was the blob, or some sort of hash. It could either be a directory or it could either be a file. And if it's a file, it's going to contain the blob hash. So here what we're going to do is make use of this. We'll have for mode, comma name, comma object hash, which is present within tree.entries. So we are looping through this list, and if we loop through the list, we get access to these three tuples, which we are unpacking over here. Now here, what do we check? The first thing we can check is the mode. So if the mode starts with 100, it's going to be a regular file. If it starts with 400, it's going to be a directory. If it's a directory, we are just going to call this function. So this function is essentially the reverse of what we've already worked on within this. So this create tree recursive, we specified the mode over here. We're just trying to reverse this process. So first we're just checking if the mode is even equal or if it begins with 100. So if mode.starts with 100, in that case, we'll just go ahead and simply say files.add name. That is the name of a file. Otherwise, we can say mode.starts with 400. Then it's a directory. If it's a directory, what do we want to do? Well, in that case, we'll recursively call this function. We'll have get files from tree recursive, but this time we'll have to specify a tree hash. And what is the tree hash going to be in this case? It's going to be the object hash, right? But also there's one edge case that we need to think about. Not really edge case, but like there's something we need to think about over here. And that is if we do get files from tree recursive, what we're doing is we're going within test, then we're going within test2. But the file name of test2 is going to be test2. But the actual file name should not be just test2, It should be test/test2. And then when we go to hello.txt, it should not be just hello.txt. It should be test/test2/hello.txt. So what we need to do is take in a prefix here. Prefix, which is going to be of the type of string, and by default, it is going to be empty. Then here I can specify the full name. So what's the full name of this file path? And then we can attach the prefix here, and then we can attach the name. And then we can say if the prefix is present, this is going to be the case. Otherwise, it's going to be just name. Or we can just leave it at this, because if the prefix is not mentioned, it's going to be an empty string, and then we'll just have the name anyways. But if you want to be explicit, go ahead, do that. After that, I can take this full name and pass it in over here in the prefix. When we actually call this function for the very first time, which we do here, files to clear is equal to this. We're not passing in any prefix because we are starting from the root. So we are starting from here. Test has no prefix. But then when this function itself calls get files from tree recursive, we want it to have test/test2 and then test/test2 /hello.txt. So I hope that's clear. Now what we want to do is, well, this function is going to return a set, correct? So what we can do is get all of the files up until here. So we have subtree files. So this will get us the files that are present within the subtree. For example, if we are on test, it will get all of the files that are present in test2. And test2 will get all of the files that are present within hello.txt. I mean, that's the only file that's present. But let's say it was hi.txt, it would get all of that. Then it gives it to test. So it's like we are starting from the very nested structure and going back up. Similar to what we did in create tree recursive. The exact same recursion logic is used here. Then we can just do files.update and then we can pass in the subtree files. The reason we are using update is because we want to take the files set and then just, add a set of files to it. And that's the function. This will give us all of the files that are present within a subtree or within a tree. Cool. Now we have files to clear. That's working out. Now after this, what we can do is, well, just do the normal checkout process. So we have moved from one branch to another. Now if you want, you can remove this current branch because, well, we already have these things initialized. So the current branch is now previous branch. We also have the current commit. So that's there with the name of previous commit hash. So we'll remove all of that. And now what we can say is, well, this previous branch should be used here. Now we have previous commit hash. So we can say if previous commit hash is present, we can do self.set branch commit, and then we can pass in the previous commit hash here. So in the new branch, we are passing in the current commit hash or the previous commit hash, whatever you want to call it. But like if we are on master and we have the commit of XYZ, for example, and let's say this was hi and this was ABC. Let's say we are on ABC and we move to a new branch. What we are doing is taking this commit and putting it as the beginning if we are creating a branch. Cool. And if you're not creating a branch, then we are simply moving stuff. So we just write to the head file and we switch. But yeah, there's more to be done here. Just before we switch, what we want to do is restore the working directory to match the branch state. So as of now, we have access to files to clear. So what we need to do is take these files to clear and communicate it with the current working directory. So understand this. What we have done here is calculated or computed the files to clear from the previous commit meaning the master branch if we are moving to the new branch. After that, what we have done is created a new branch, or let's say managed a new branch, whatever, by using all of this code until here. This helps in supporting like moving to a new branch. After that, what we want to do is restore the working directory as well as remove the files that don't matter, add the files that matter. So in our case, when I gave the example of branch1.txt and branch2.txt, what should happen is that when I move from master to branch1, these files should remain, branch1.txt and branch2.txt. But when I move back, these two files should be deleted. So these two files are calculated, the branch1 and branch2 are calculated when we do this thing. Think about it. We go to this branch, we calculate the latest commit that we have. The latest commit includes all of these things, main.py included. So all of the 3 files. Now we go to master, we calculate its thing. So what are the files that are present within master? And then all of the differences should be resolved. So here I can just create a function called self.restore working directory. Here I'm going to pass in 2 things. The first one is the new branch that we are on. So this branch variable, because obviously we have a new branch that we want to check out to. So I'm passing in the new branch, and after that I'm also going to pass in the files to clear. After that I can create the function restore working directory. After that I'll have self branch, which is going to be a string, and then we're going to have files to clear is equal to none, and its type is going to be a set, or let's say an optional set now. And optional needs to be imported from typing. So first things first, what we are going to do is get access to the commit of the latest branch that we are on, the newest branch. Let's call it the target branch. So we'll get access to the target commit hash. So we get self.getBranchCommit. Then we'll pass in the current branch, which is just the branch. Now we have the commit hash. Now we want to get the object out of it. But before we do that, I'm just going to check if not target commit hash, then we return. There's nothing more we can do if the hash of the commit does not exist in the first place. After that, I'll have the target commit object, which is going to be self.load object, essentially what we have done before, like all of these things. So this is what we want to do again, but for the new branch. So the target commit hash will be there. Then we access the target commit, which is equal to commit.fromContent. And then we pass in the target commit object.content. So having done this, there's one other thing we want to do before this actually. So let me just go here. So after we've calculated that the target commit hash is present or not, I want to remove the files that are tracked by the previous branch. So like these things, I want to traverse over all of the files to clear and then remove it. So what I can do is for all of the paths, and all of them are going to be relative paths in the sorted list of currently tracked files, which are files to clear. And by the way, files to clear can be set or null. And actually it can only be a set, because here we are ensuring it's always a set. Because even if it's an exception, we get an empty set. So we can just change this to set, and we won't give it a default value of null. Now what we can do is for all of the relative paths that are present in files to clear, because remember, when we calculated the files to clear in this function, what we did is like this. We have the test folder, we have test2, and then hello.txt. It's a relative path. It's not an absolute path, because to create an absolute path, we'll have to do git clone. And before that, we'll have to specify where we are. We are in the desktop. And before that, we'll have to specify other details. So from the root, where is this thing? That's the absolute path. And that's what we want to get, the absolute path, so that we can remove those things. So now what I'm going to do is here for all of the relative paths, I'm going to attach and create kind of the absolute path. So we have the absolute file path, which is equal to self.path. You remember that? Self.path contains the actual folder that we are in, the git clone folder, the absolute path to the git clone folder, and then we can just pass in the relative path. And now we can just say if the file path dot is file. If that is the case, then what we want to do is file path dot unlink. Unlink is a function that's given to us. Also, we don't get this autocomplete because it doesn't know that file path is going to be of the type of string. So here we can just say set of string is going to be present. So now we know this is going to be a path. And what unlink does is that it removes this file or link. And since each of the things that are present here is going to be a file, we remove it permanently from the directory. That's what we're doing here. And obviously this can be error prone because like all of these are path related functions. And if any one of them errors out, let's say there's some issue or something, we don't want the entire process to fail. So we are going to silently handle it. We are going to do try and except. So just in case one of the files is corrupted, for example, and it's not able to unlink properly, we can do nothing about it. So we just silence out the error. So this would help us to continue the process despite one error happening. Now that we have removed all of the files that are tracked by the previous branch, I can go ahead to the target commit and get its tree hash. So I'll do if target commit dot tree hash is present, then what we want to do is, well, restore the tree that's coming out of this tree hash. What this function does is that it recursively restores the tree to the file system. It's not doing any of the things that you would have any other function do. All this function is doing is going through the tree hash and then actually spitting it out in the file system over here. So let's create a function of restore tree. Here we'll pass in the tree hash and we'll also pass in the root directory path. Or actually we don't need to pass that in, we can get access to that in the function itself. And tree hash is obviously going to be target commit.treehash, all right? Let's go ahead and create this function. So we have def restore tree, and this restore tree function is going to look very, very similar to the recursive tree function. So let's go to the recursive tree function and copy it entirely because it's very, very similar. We are doing similar stuff, but here we are actually going to write to the file system. So what we do is, well, remove this file set because we don't need to keep a list of sets that are present anymore. We directly need to write to the file. That is the main difference between the two functions. One is just trying to create a set so that it can be given to the caller function. The other one, which is this function is trying to write to the file system directly. That's why we can't use the get files from tree recursive function. Now what we do here is load up the object, then we get access to the tree, then we loop over all of the entries. That's great. And now instead of full name here, I want to get the absolute path. And to get the absolute path, we can just say the entire file path is going to be self.path followed by the name of the file that's present here. Then we can check if the mode starts with 100, then it's a file, so we need to do something about that. But if it's a 400 starting with, then we want to recursively call this function. So we just do self.restore tree. We pass in the object hash, but here, if you remember in the recursive function here, we needed to pass the full name. So that would be the prefix. And then we would attach the prefix here so that test/test2/hello.txt could happen. In this case also, we need to do a similar thing, but we need to do it with the path. So the path needs to be passed in here instead of the full name. So we pass in self.path/name. So in the first instance, we get the absolute path to test, then we get the absolute path to test2, and then hello.txt. Essentially, like, we need to pass a prefix here, but the prefix is not going to be a string. It's going to be an entire path. And that's why what we're going to do is, well, accept a path here. And when we call this function, the restore tree function here, I'm going to pass in the self.path here as well. Because the first time we call it, we are doing it for the root folder. So we are going to pass in the current folder that we are in, git clone. That's self.path. And then the next time, the path can be used here. Instead of self.path as the prefix, the path will be used as a prefix. So the first time, how it's going to be is something like this. You have users, you have /Revan, then you have the desktop, then you have git clone folder, then you have this file name, which is test. So this was the path, all right? This entire thing is the path. Now we attach the test folder to it. So now this is the file path. Then we know test is going to be a directory. So it calls this thing, it restores the tree, passes in the file path. So it passes in this entire thing. to this function. And then again, when we go through this tree's entries, we get test2, and test2 is going to be created with path /name. So it's going to be test. Well, this is the entire path now. And then what you can do is test2, because that's the file name that we are concatenating. So that's what we're trying to achieve. So with this, we are able to restore the tree, but we don't want to do this. And before we call the restore tree function, what we need to do is create a path. So here we have access to the file path. So I'll just do make directory exist OK is equal to true. So if this folder already exists, that's fine. Don't throw an error. And then I can call the restore tree because, well, since this is a directory, we'll go ahead and create the test folder if it doesn't already exist. Then we restore the tree, so it goes to test2. We'll create a folder for that as well. And then finally we come to hello.txt, and for this, we'll have to do some things. So the very first thing is that we know it's a file. If it's a file, we know what type it's going to be of, a blob object. So we can go ahead and extract the blob object out of this. So we have self.load object, and then we pass in the object hash, because we know this object hash is going to be the blob object. After that, we can create a blob out of this blob object. So it requires content to be passed in. When we do blob object, we get blob object dot content. Now we have the blob specific thing. And the only thing we want to do here is file path dot write bytes. And here I can just pass in the blob's content, correct? So I can just pass in blob.content, or I can pass the blob.getContent. Both of these things return the same thing. So what I'm going to do is go back to blob and remove this function. It's so useless because all we're doing is returning self.content. It's not needed. And I can just do blob.content, and that's it. So with this, what we're doing is writing to the specific file path. So we are writing to test2 hello.txt, and this way we are restoring the content back to the file system. And then when we call this function, restore tree is called here. That's great. So the content is back in our file system. Now there's one more thing that we need to do, and that is we want to clear off the index in our thing. So as of now, what's happening is that we check out, and the entire checkout process is first we get all the files that we need to clear off, then we move to the new branch, then we clear off those files, and then we restore all of the files in the new branch. But now here's the issue. What if we were on the master branch, we made some changes, but we did not commit them? Okay, the real Git would handle this by giving you an error that, hey, first you need to commit your changes or remove your changes, and then only we can proceed. But we're not adding that check. Adding that check is very useful. So go ahead, add it on your own. If you're able to do it, that means you've understood the tutorial so far. It should be something like checking the index. If the files are present there, then you just give out an error before checking out. But what I'm going to do is assume that the user is smart enough that, they committed. So I'm directly going to say that self.saveIndex empty. So I'm going to clear off the index no matter what it is. And actually this should happen no matter whether the user has a tree hash or not. If the target commit has a tree hash or not, irrespective of whether that happens or not, we need to save the index to be empty. So yeah, that's the entire function. Let's go ahead and test it out. Before moving forward and testing out the checkout option now, what I want to do instead is just fix one bug that I noticed. And that is in the get files from tree recursive function, what we are doing is that we are adding files.add name. But I told you we don't want to add the name. We want to add the full name here. Correct, because we also want the prefix to be there. So in our case, test2 should be there. The entire path name should be there. So we need to add the full name here. And for this one, when we do get files from tree recursive, we are passing in the prefix. So the prefix is this entire thing. But is that enough? So we have test in the very first case because we don't have a prefix, because we are starting from the root folder, right? So we have test written out. The prefix is empty, so it's just test. Then we pass that test over here, so the prefix is test, followed by the name. The name is test2. So we don't want to do this, correct? We want to do test/test2. And that's why what I'm going to do is here, we're going to pass in the prefix as this string where it's an F string, so the variable full name is passed forward by the /. We can save this. So that's one debug. And the second one is I would like to remind you that we're using .git throughout, correct? I'll stay with .git, but I would recommend you to not use .git. Instead, use the .pygit version, because if you're using GitHub to actually store your project, it will cause some inconvenience. That's why just make sure you have .pygit. But what I'm going to do is go to my entire reveal and finder thing. And from here, I'm going to uninstall .git and .pygit, both of them. So we are going to start fresh and step by step add all of the things. So the very first thing is I would like to add this entire directory, but I'm going to remove the branch1.txt, all right, and branch2.txt. Or actually I can keep branch2.txt. So in the first commit, the master commit, I'm going to add all of these files. So let's go ahead and add it. We're going to do python3 main.py init, because we have deleted our Git repository. After that, we're going to do add the entire folder. So we've added 6 files from directory now. So that's these files, each one of them. After that, I can do python3 main.py commit -m, and I can say all except branch1.txt. So I've committed on the master branch. Cool. Also, one cool thing I would like to show you is that our VS Code picks it up, because I've done the changes in .git, right? So here it says 6 files changed, 557 insertions. It's automatically able to figure it out. So that's pretty cool. We've not exactly replicated Git, so some of the things might not work, but it's very cool to see that it's able to figure out everything. So like all of our insertion, all of the files, and the commit message, and even the username, and even the time. So all of that is working. You know, our commit data is actually working because we are using the same hash as they do. But either ways, the VS Code source control works. So that's great. Now what I like to do is shift to the new branch. So when I shift to the new branch, what's going to happen? Well, I'll do checkout -b new branch. So we create the new branch, switch to the new branch. So our commit from master has carried out to this new branch. Now what I'm going to do is create a new file. Let's call it branch1.txt. Hey, this is new branch1. So I'll add that. Then I'll go ahead and add this file. But notice when I do add over here, it says added 7 files from directory. It should not be doing that. It should technically only be adding 1, right? Because we changed nothing else. We just added a new branch1.txt. So there's only one file that changed. So it should only capture that one branch. But moving forward, we can just do commit -m and we can say branch1.txt. Cool, we've created that commit. Now what I'm going to do is move back to the master branch. So we have checkout master. And once I do that, you can see branch1.txt disappeared. That's because master branch does not have branch1.txt. Only the new branch has this commit. So it removes it completely. Now what I'm going to do is again check out into the new branch, and we should have branch1.txt appearing over here. And it does appear with the same content. So that means our checkout process is working as expected. You should be getting this output now. Now I'd again like to go back to master, and here I'm going to create a new file called branch3.txt and call this, hey, we are having branch3.txt. Now I'm going to add this file, because if I did not add and commit, and let's say I directly move to the new branch, so I check out to the new branch, this file will be lost. It won't be there because we are clearing off everything. correct? We remove the file from the file system, index does not keep track of it, nothing. And that's why I told you to implement this and see if you can do it on your own. But now what I'm going to do is add all the files again. So as you can see, it adds 7 files from directory again. It should technically only be adding 1, but the way we work, we just add everything together and we don't check if the files from the previous commit match the files in the current staging area that we added. So essentially it's not comparing that, hey, branch2.txt has already been added in the previous commit, so we don't need to add it anymore. No, it does not do all of that. It just directly goes ahead and adds it. And the counter is also added. So if you want to fix that, you can do it, but I'm fine with it. I'm cool with it. After that, I can go ahead and commit. So we have commit -m, cool. So it creates a new commit. Cool also shows up again. That's nice. Because that's nice because as you can see, even VS Code knows about the branch history here. It knows that cool's previous commit is all except branch1.txt. So it's very smart. And this linking will help us. If even VS Code knows that the previous commit of cool is this all except branch1.txt, it means that when we try to display the status, so when we implement the git status command, it will be very easy for us because everything is working as expected, right? Now what we can do is, check out to the new branch. And once we do that, as you can see, branch3.txt is deleted now and branch1 is automatically added. So that's the entire checkout process. I would again like to get back to the master branch. And by the way, if you click over here, you'll notice that we have a master branch and a new branch. So the branches is done properly because we are saving it to refs and everything. So that's very nice. I'll just check out to master again. And with this, we have completed the checkout function. Now what I'd like to do is go over this again so that, we have a concrete understanding of what's happening. So the very first thing we did is compute all the files to be cleared from the previous commit. The previous commit as of now is like, we get the current branch, or it should not be from the previous commit. It should be from previous branch. So we get all of the files that are present within the previous branch. So to get it from the previous branch, we need to check all of the files that are present within the previous branch's commit, the latest commit of the previous branch. So we get the current branch, then we find out the previous commit hash, then we load up the object, we create a commit and then get its tree hash. And based on the tree hash, we are getting the files, correct? So this is our entire logic. I've explained this to you, so I won't spend time, but it's a recursive function. And what we're doing is recursively adding all of the files that might be present, like branch 2, branch 3. We create the test folder based on whether the mode starts with 400 or not. We add the file based on whether the mode starts with 100 or not. Cool. So that's the get files from tree recursive function. A similar logic is also applied later on when we go to the restore working directory. But with this, we have figured out what are all the files in the previous branch that we want to remove, because we'll be removing all of the files and then we'll be fetching all of the files from the new branch. Now there are obviously optimization techniques you can figure out over here. For example, just compute the files that differ and only change them instead of removing everything. And I'm sure there are various other approaches, so you can figure that out on your own. But at the very base layer, this is what we're trying to do. Then we create or move to a new branch based on whether the flag is set or no. So if the branch file does not exist and create branch is done, we go ahead and create a new branch. Otherwise, we just say that this branch does not exist. Use this command. Then we update the head file. So the head file here in .git/head is at master, but when we check out, it will be new branch. Then we restore the working directory. Restore the working directory means we'll be actually clearing off all of the files tracked by the previous branch. And we do that via unlink. And if file path.is file, we are unlinking. But there's another check you can put, which is elif the file path is a directory, correct? If it's a directory, then what do you want to do? Well, you want to check here if the directory is empty. If the directory is empty, then you want to remove this directory completely. So here you can just check if any file path dot iterate over the directory. So it iterates over the files in this directory, does not yield any result for the special paths this and this. So essentially like going over the entire directory. If that is not present, so if not, so that means this returns an empty list. So you go over the directory and you do not find any files. What you can do is file path dot remove directory, because it's an empty directory. So that's something you can do. I'll just comment it out. So if you look at my source code, you'll be able to do it. So uncomment if you want this functionality, and this functionality is like removing empty directories. After that, what we're doing is get the target commit object. So what we're doing is we've checked out to the new directory, right? Like to the new branch. So we are trying to load the latest commit object of that branch. And once we do that, we take its tree hash and restore it. And we call the restore tree function for it. And all it does is very similar to the recursive function, but instead of creating a set of files that need to be clear of, what we do is actually write to the file system. So if it starts with 100, we are actually writing to the file system. Especially this line is what makes everything happen. And if it's a directory, we automatically create the directories. So that is our entire checkout logic. And now since we're already familiar with the branching logic and the revision, what I'd like to do is work on the branch command. So here we have the checkout command. We also have the branch command, correct? So I'd like to work on that now, because branch command allows us to list the branch, create a new branch, or delete a branch. So listing the branches should be easy. All we have to do is go to the refs, which is this particular thing, heads, and list out all of the files that are present here. Master and new branch. These are all the branches. And then we also want to highlight what is the current branch we are on. And we can do that by checking out the head file, because head file is going to tell what branch we are on. To delete a branch, all we have to do is like remove the branch from this refs again, refs, heads, and this. So like that is very easy. And to create a new branch, we already know how to do that. We have already implemented it in checkout itself, this particular thing. So since we are fresh with this, let's go ahead and get done with this. So we have a branch command. So we'll have a branch parser here, which is equal to subparsers dot add parser, and then I'll pass in the branch. Then we have a help command, and the help command is going to be that this command helps us to list or manage the branches, all of the branches that are present in our git clone. Then we can take this branch parser and add the arguments. So the very first argument is -b. The second one is -- branch. You either pass in -b or you pass in -- branch or create branch. Let's call it create branch. If either one of them is done, we can do action is equal to store true, similar to what we did here. And we can just say the help message is going to be to create a new branch. Great. After that, we'll again add another argument, which is going to be branch parser dot add argument. And then we'll do -d. Then we'll again do -- delete. So it helps us to delete. And then we have action is equal to store true, and help message is going to be to delete the branch. Great. So that looks like we have added support. So we can simply go here and do lfags.command is equal to the branch. In that case, we will check if the repo.get directory does not exist. We just print out this message. Otherwise, we'll do repo.branch, and then I'll pass in the args.branch or args.name and args.delete. And I think we have not added an argument of name, because the user also needs to specify the name of the branch, correct? Yeah, let me add that. So we have branch parser dot add argument, and this will be name. So what is the name of the branch? And the nargs here, the number of arguments, is going to be question mark. So it can either be present or not present. And if it's not present, that means the user just wants to list out all of the branches that are supported in Git. And if they do mention the branch name, that means they want to either move or create a new branch. So I'll just remove this -b. So if we do git branch with the name, let's say git branch hello, it will create a new branch if it does not exist. And if we do git branch, let's say the name of the branch followed by -d, it will delete the branch. And if we just do git branch, it will list out all of the branches. Great. Now let's go ahead and create a function called branch. So we have def branch, we'll have a self, then there are two arguments. One is the name of the branch and the second one is if we want to delete it or not. So we take in a branch name, which is going to be of the type of string. And then we also take in a delete boolean option. By default, it is going to be false. And then what we can do is check if delete is true and the branch name is present. That means we want to actually delete the branch. So what we are going to do is set up the branch file to delete it. So we have branch file is equal to self.heads directory followed by the branch name. So what we are doing is going to the heads directory here, going to this new branch, and as you can expect, we're going to delete it. And we know how to delete a file. For that, we can just do if branch file dot exists. So if this exists in the first place, what we are going to do is branch file dot unlink. That's what we did in the checkout as well, if we wanted to delete a file. And then we can just print out that, hey, we deleted the branch with this branch name. And if this branch file does not exist, we can just say, hey, the branch that you mentioned, this branch name, not found. And let me just pass in the branch name here. After that, we're going to check if the branch name exists. That means we want to create a new branch. And also this should be in the else block because the first one is delete. So we are actually checking if we want to delete or not. And if we don't want to delete, that means we'll check if we want to create a new branch. And this ordering is quite important, all right? Because if you first check if branch name, so if you first carry out the functionality of creating a new branch, that would mean you ignore delete. So even if the user says delete, you'll always do the creating new branch first. For example, if you do git branch -d hello, okay? And if you have this condition, what you're checking is if the branch name is present. Yeah, hello is present. So in that case, you just go ahead and carry out the operation related to creating a branch. But that's not what it says. It says to delete. And that's why first we have to check the delete operation. That if delete is mentioned and the branch name is present, then we want to do something. And actually, instead of nesting it out, what I'm going to do is return. So if we delete stuff, we're just going to return out of this function. That's cool. And then if let's say the delete option was not mentioned, only the branch name was mentioned, that means we want to create a new branch. And for that, we have our code. We have current branch is equal to self.getCurrentBranch. So once we get the current branch, we are just going to get the current commit, which is equal to self.getBranchCommit. Then we pass in the current branch. I'm going really fast on this one because we have already implemented this in the checkout part. But just to get extra practice, I'm not copy pasting it. Then we just check if the current commit is present. Then we self.setBranchCommit to be the branch name. And then we pass in the current commit as well, because our new branch is going to start from the previous branch's commit. Then we can print out that, hey, we created branch with this branch name. Otherwise, let's say the current commit is not present. So we can just say that, hey, no commits yet, so I cannot create a new branch. Sounds good. Now let's say the branch name is not there. So if branch name is there, we do all of this. Let's say the branch name is not there. Then we want to list out all of the branches. We don't want to create a new branch. We're listing out. So we have current branch is equal to self.get current branch. So if you want, you can just pull out of here and just create a current branch variable at the top, because it's used in if and else both. Then we can just have branches is equal to an empty list. And then we go over all of the files that is present in the heads directory. And to do that, we can just do for branch file in self.heads directory.iterate directory. So we iterate over all of the files that are present in the directory. And then we can just check if the branch file is file. That means it is one of the files like master or new branch, because we don't really have support for anything else. For example, let's say in our heads folder, we had some other folder. Now that's pretty unlikely, but let's say it was the case. So we're just handling that. And then we can just do branches dot append. And then we say branch file dot name, because the name of this file is going to be the branch name. And after that, what I'm going to do is loop over all of the branches that are present within this branches thing. Also, I'm going to sort it, because I like consistency. And then I'll print out the branch. But that's not enough, because if I do that, I'm listing out all the branches, but I also want to tell if this is the current branch or not, which is why I had created this variable called current branch. I want to track if this branch is the current branch we're on. And that's why what we're going to do is convert this into an if string. Then I'll have a current marker, which is equal to, well, an asterisk if the branch name is present, and if the branch name is equal to the current branch we're on. Remember, get current branch is also going to return to us the name of the branch. So it can be compared. It's not returning the hash or anything like that. It's directly returning the name of the branch. So we'll just do that. Otherwise, we leave some space, and yeah, we maintain that indentation. And we actually have to leave 2 spaces to maintain indentation, because here there's an asterisk and a space. Here we leave 2 spaces so that, everything is indented properly. Now what I'm going to do is, carry out everything is done. We can just do branch, and for some reason it prints out .dstore, but also I have forgotten to put the current marker here. So I'll just put that in. Let's do it again. And it does point out correctly that master is the branch. And the reason it prints out .dstore is because this folder contains a hidden file of .dstore. So that's another edge case we have to keep in mind. So here we can just say if it is a file and the branch file dot starts with, and actually I need to convert it to a string, which would be branch file dot name dot starts with, and let's say it starts with dot. So if it does not start with dot, only then do we add it to the branches list. And now if I run it, as you can see, we only get master and new branch. Earlier it was not filtering out the system related files, which is .dstore. So yeah, we're all set. Now let's go ahead and delete one of the branches. So I'm just going to go ahead and delete the new branch. Then let's say I list out all of the branches and only master appears. The file is gone from here. And let's say I want to create a new branch. I can go ahead and create a new file called new branch. And if you look at the content of new branch, the commit hash will be the same as the commit hash of master. So everything works out as expected. That's great. And with this, we have also implemented the branch functionality or the branch feature. The next feature we want to look at is log. So if we do git log, what happens? To understand that, I can just go back to our folder of git test. And here I'm just going to print out git log. So here, what does it print out? It prints out the commit that is present. essentially a list of commits that is present. So git log is kind of like this version control system. For a specific branch, it will list out the commits. So it will print out this commit, author information, date, and the message. Seems fairly easy to do considering we have all of the building blocks for it, right? That's because we know from the commit how we can boil these or get these fundamental information. So we can get the commit, we can get the author name, and then we can get the date and also the message. So we know how to boil everything down. Should be very, very easy actually. So let's go ahead and implement it. So what I can do is create a log command here. So we have log command. Then we have log parser, which is equal to subparsers dot add parser. And then I can just do log. Then the help is there, which is, well, what does log do? It shows us the commit history. So yeah, I'm fine with that. Show commit history. And after that, I can just add an argument here. Log parser also takes another argument of how many commits do we want to show. And that can be set up by doing -n or setting up --max count. So what is the maximum number of commits you want to display? So the type here is going to be an integer and the default is going to be 10. We're going to display a max of 10, but if you want, you can increase it to 50. And then we can just say that the help message is limit commits shown. And then I can also have a help message here. That's great. Now what I like to do is add a support for this command. So we have elif args.command is equal to, and I misspelled it, command is equal to, let's say log. In that case, again, we're going to check this thing. So if you want, since this piece of code is being used everywhere, you can create a reusable function out of this, clean code practices. And then you can just do repository.log. And then you'll pass in the max count if it's mentioned, by default, it is going to be 10. So max count is obviously going to be there every single time. So yeah, max count is mentioned here. Sweet. Now let's go ahead and implement it. So we have def log, we have self, and all we do is take a max count, which is of the type of integer. And if it's not mentioned, it's going to be 10. And it is always going to be mentioned because max count is always 10. Like by default, we have set it to 10. Now, how do we show the commit history? Well, we show the commit history for a specific branch, correct? So the very first thing we have to do is get the branch we are on. Then from the branch, we can get the commit hash. And based on the commit hash, we can go to its previous things or its parent hashes to display that. So first thing is the current branch. So we have current branch is equal to self.get current branch. Now based on this branch, we can get the commit hash. So we have commit hash is equal to self.get branch commit. Correct? Now we'll just check if this commit hash is even present. If it's not, then we can just say, hey, there are no commits yet. You're too early. And then we return out of this function. Don't execute it any further. But if the commit hash is not present, then the count is going to be 0. Why? Because now we are going to count from 0 to max count and display all of the commits. So we can just say while the count is less than max count, then we want to implement the logic for traversing all of the commit history. To traverse the commit history, by the way, we can go to the commit class, which is this thing. Here we have parent hashes, right? Parent hashes contains the commit hash, the parent commit, the previous commit that was done. So for one commit, we can go to its parent hash. So let's say we have a structure that looks like this. These are, each node here is a commit hash. So what we are doing is we are on this specific commit. We go to its parent hash. So we are on this commit, then we go to its parent hash, then we are on this commit, and we keep doing that. And that's how we get the entire commit history. So let's go down to our log function and here implement it. But also there's an edge case. We just do while count is less than max count. But what if the number of commits is less than 10? What will happen then? because whatever logic we implement here of going backwards, so this logic of going backwards in history, it will keep running as long as count is less than max count. But at one point, let's say we have only 5 or 6 commits. In this case, we have only 5 commits. It's not 10. So it will still keep executing this, and we don't want that. So what we are going to do is while commit hash and count is less than max count, so that, we don't run out of commits and it doesn't error out. So while the commit hash is present and the count is less than the max count, what we are going to do is create a commit object. And commit object is going to be to load the specific object based on its commit hash. So we have the commit object, and now we can create the commit from content, and then we can do commit object dot content. So now we have the commit object created. We've done this many times, so I'm not explaining it, okay? All of the things other than add and commit are like straightforward, because you have to use all of the building blocks to just place them correctly. You kind of have the Lego pieces with you. You just have to create the building out of it. Now, since we have the commit details with us, we can go ahead and write details about this commit. So the very first thing is the commit hash, correct? So I'll just write down the commit hash here. Then the author name, which is, well, simply author, and then commit dot author. After that, we are going to get the date. So the date is going to be time.ctime. By the way, we are not using time.time because it converts a time in seconds since the epoch. So we're going to pass in an integer value here, and it will automatically convert it. If you want a nicer formatting, go ahead, do it on your own. I don't mind. Then we can just do commit.timestamp. And finally, after all of this, we print out the commit message. And if you notice, the commit message is on a new line. So like we leave a line and then we go and type out some message, and even the message has some indentation. So let's copy that indentation, paste that here, and then I can say commit.message, and then I would like to leave a line so that there's some spacing before the next command. But if you don't want to do that, that's fine. After that, we want to move to the previous commit, correct? And to do that, we can do commit hash is equal to commit dot parent hashes, and we access the 0th index of this parent hashes. So we remember that parent hashes is a list, but in our case, it's very simple. The list is always going to have one element. We're not implementing the merge feature such that, we have 2 parent hashes. We have only one. And here we can just say if commit dot parent hashes is less than 2, the length of the commit hashes is less than 2. Or what you can do is just check if commit dot parent hashes is present. Because if commit dot parent hashes is present, that means it's not an empty list, because that's what it checks. If you do this line, it's checking for empty and null. So we can just say if this commit.parent hashes is not empty, we can just do commit.parent hashes at 0. Otherwise, we will say that commit hash is null, and this will evaluate to false. So in the next iteration, nothing will happen. Also remember to do count plus equals 1, so that just in case we reach max count, we get out of this loop. Cool. So that's our entire log feature. Let's save it. Let's open it up. I'm going to do branch because I want to ensure that I'm still on the master branch. You notice that when we do branch, new branch, we're not actually moving to the new branch. We just create a new branch. When we do checkout -b new branch, we are creating and moving to a new branch. So that's a good detail to keep in mind if you didn't already understand Git. And now we will just log. And once we do that, it says error get branch commit missing one required positional argument. And yeah, that's true because I've not passed in the current branch here. So I need to pass the current branch to get branch commit. Now I'll do it again and it says no commits yet. And that happens because we have another bug. And that is if the commit hash is present, we are saying no commits yet. That's not true. If the commit hash is not present, we want to say no commits yet. And that was a good indicator, by the way, because if it says no commits yet, that means there are commits and we have done exceptionally well. So we have printed out our first commit, all except branch1.txt. We've printed this out and it correctly prints out the time as well. So it does 10:12:53, 10:07:17, and that's the exact time. That's about 40 minutes ago. That's good. So that is the log feature, and yeah, we're almost done with the entire tutorial. The other command that we want to support now is status. That's the only one we are left to support. And status is also not that complex. I mean, there are a lot of moving parts in it because there are multiple things we want to keep track of. But I think we have all of the building blocks. Almost all of them. We'll probably have to create one or two functions to get the status working. But yeah, it should not be very difficult. So let's get started with the status part. So the first thing that we're going to do is just add the support for this command in main function. So let's go ahead and create a comment saying status command. And then what we're going to do is create a status parser, which is equal to subparsers.add parser. And the name of this is going to be status. Then the help message is going to be show repository status. After that, we can go down here and have elif args.command is equal to status. In that case, we are going to do the following. First, we are going to check the same thing, if it's a repository or not. And after that, we are going to call the function repo.status. And we are not going to pass in anything because, well, if you call status, all we want to do is display the status. We don't take any input arguments as such. After that, we can take the status function and, well, create it in the repository class. So here I'm going to create a function status self. And well, what is this function going to do? What does it mean to show the repository status? It means that we'll display what the branch is. So what branch we are currently on. Then we are going to display what files are staged for commit. What does this line mean? It means that, we have three working areas as we learned before. A working directory, staging area, and local repository. So what files are present in the staging area that are ready for committing? Then we are going to display what files have been modified but have not been staged. So let's say I do git add on main.py and then I edit main.py. So I've not added the updated main.py to the staging area, but I have the previous version of main.py that's added. So it will display that. Okay. After that, we are going to display what files are untracked. That means they're not present in the index, or let's say they're not present in the staging area and they're not present in the commit either. So they are called untracked files. And finally, we are going to display what files have been deleted. So these are the things we want to work on, and it's fairly straightforward, but we do need to figure out a bunch of things. So first things first, let's display the branch information. So let's go ahead and create current branch is equal to self.get current branch, and then we are just going to display it. So we are going to say printf on branch, and we are on the current branch. Cool. So we have done step one. Now step two is what files are present or what files have been staged for commit. So they're in the staging area, and we know staging area directly relates with the index. So what we are going to do is load up the index. So we have index is equal to self.load index. Now we have a dictionary with us, but the thing about index is that it will be used everywhere else. It's also going to be used in what files have been modified but not staged, because we need to figure out that the file has been modified, but it's not in the index. So we have to check if it's present in the index or not. So what I'm going to do is just put it above, because it's quite a reusable variable. I don't want to put it within a specific commit or within a specific comment. And now you might think that what files are staged for commit can only be done by doing looping through this index and figuring out all the file names. And we know in the index, which is present in .git and the index file, the mapping is something like this. So you have the file name. So a certain file name will be present followed by the hash. So that is the index. So you might think that we can just pull out all of the keys and those are all the files that are staged for commit. But that's not totally correct, because in our implementation, we can add an updated file as well. Let's say we commit a particular thing. We do git add main.py and then we commit it. And then we again do git add main.py. Our git add will add the main.py file. It will not check that, yeah, it was present in the last commit, so we cannot add that to the staging area again. No, that's not how it works. So that's an edge case to keep in mind. If the file in the last commit that we had has already been staged and the file has not modified, then we don't want to display it over here. So what I mean by that is, let's say I do something like init and then I do add main.py. So after I add main.py, what's going to happen is that I will commit. So I will commit this main.py. Then I don't make any changes to the main.py file. I again do add main.py and it will succeed, because in our add function, we're not putting in any checks whether main.py has been committed already or not. That's why here, after this point, if we do status, and in the status, if we just display the file keys that are present, so the keys present in the index dictionary, it will spit out all of the files, which is main.py, but we should actually not show that because it's not actually staged for commit, right? So what we are going to do instead is figure out the last commit that we made, what were the files included in that, and then we'll add to the staged thing. Cool. So for that, first we need to figure out the current commit on the latest branch, right? So for that, we will just do current commit hash is equal to self.get commit or branch commit, and then I'll pass in the branch we are on, and we know that the branch is this one, so I'll pass that in. Now I have the current commit hash. So based on the commit hash, I want to figure out all of the files that are present in this commit. And to do that, we have done this many times before. So all we need to do is figure out if the current commit hash is null or not, because it can be null, right? After that, we're just going to do try and except, because even if there's a possibility of failure, we won't accept it. And what exactly are we trying to achieve here? Well, we are trying to create a mapping between the files and the hashes. So essentially what we are trying to do is build the index of the latest commit. That's what we are trying to do. This index is of the latest thing right now. So when we commit, what we're doing is clearing off the index. So this is that one. So any new things are added after the last commit will be shown in this index. This index helps us build the new commit. Cool. Now the index that we are trying to build is of the latest commit, the commit that has already been done, or you can call this the previous commit. But technically it is the latest commit because we have still not committed, right? Because if the index does not have files, that means those files have probably not been committed. So what we're trying to do here is just build the index of this commit hash. And then what we'll do is compare this index that we create with this index, and that will give us all of the files that are staged for commit. Now let's go ahead and create the variable. Let's call this last index files, which is equal to an empty dictionary. Then if the current commit hash is present, or actually if there's a failure, let's say there's an exception, what we do is just initialize it to an empty dictionary. We silence out the error. I've talked about this before. And then what we are trying to do is create the commit object, which is equal to self.load object, and then we pass in the current commit hash. Cool. Now we have the commit object, and now you know what we want to do. We want to create an actual commit, which can be done using commit.from content. Then we'll pass in the commit object.content. And now we have access to the commit. Now, how do we build an index from the commit? For that, obviously, we have one thing that we can use, which is the tree hash, correct? Because tree hash contains all of the information about the files and the directories that were used in the commit or that were committed. So based on the tree hash, we want to build the index, and we don't currently have a function that does it, but it's going to be quite similar to many functions we've already created. So let's go ahead and create a function called build index from tree. It's going to be requiring self. It's going to require a tree hash, which is going to be of the type of string, and well, a prefix, which is of the type of string, and it will be empty if not specified. And the rest of the logic is going to be quite similar to the function we've already worked with. And the function I'm talking about is the recursive function that we had created, get files from tree recursive. So let me just copy this entire thing and paste it down here. I do think since the logic looks quite similar, you can create some sort of abstraction and use a reusable function instead of creating 3 or 4 functions that look quite similar. Go ahead and do that. That would be great practice for you to write cleaner code as well. So the first thing that I want to change here is that we'll remove the set. We are not looking for a set. We are trying to create an index, which is a dictionary. So we'll have an index here. Then we have the tree object that's created. Then we go over all of the entries in the tree. We create the full name. That looks good. And then we say that, hey, if the mode starts with 100, in that case, it's going to be a file. And if it's a file, then we obviously add it to our index. So index at full name is going to equal to the hash, correct? And the hash is going to be the object hash, because that's the mapping we are trying to create. File name to the hash, that's the mapping we're creating. And if the mode starts with 400, it's a directory. And if it's a directory, what we need to do is build index from tree. Then we'll pass in the object hash. We'll pass in the prefix, which is going to be the full name. That's it. And then this will give us the sub index, or whatever you want to call it. But essentially, it's going to give us a dictionary containing the index, right? Because from here, we are returning the index. So as soon as this recursive function gets over, we will get the mapping of the dictionary, and it will be certain element like this. So what we want to do is take the subindex and add it to our main index. And to do that, we can just do index.update, and then we'll pass in the subindex. Great. So yeah, that's pretty much everything. So we can take this function and call it in the status part. So here we will call self.buildIndex from tree. We'll pass in the tree hash, and the tree hash is going to be commit.treehash. The prefix is not going to be passed in. It's going to be an empty string. And this is going to return to us the last index files, which is equal to this thing. So we're all set. Now what I want to do is figure out all of the staged files. And to figure out the staged files, we have to compare the index that's created here with the last index files. So let's go ahead and check it. So the first thing I'm going to do is make a union between the index.keys and the last index files.keys. So as we remember, the keys are the file names, correct? So in the index, we have the file name as keys, and the last index files, the keys are the file names. So what I want to do is get a list or a set of all the file names. So I'll just do the union between this index and the last index files. All of the duplicates will be removed then, because I'm going to convert it into a set, and then we can compare it for each one. So the first thing is just figuring out file path in set. Then we'll do index.keys, and we want to unify this or do a union with the last index files.keys. And I actually have to do it outside. So we have set of last index files.keys. The only reason we're converting it to a set is because we want to call this union operation. By the way, union operation means if you have a dictionary that looks like this, or let's say you have a list, because we are trying to compare the list, right? Index.keys is going to give us all of the file names present in the dictionary. Even this is going to give us all of the file names present in the dictionary. So let's say I have main.py, I have test2.txt, and we're doing a union with, let's say, hi.txt and main.py. What we are doing is converting it into a set, because the union operation is not present within a list. The union operation is only there for a set. And we do the same thing over here. After this, we can do the union, and the result of this is going to be main.py, test2.txt and hi.txt. the duplicate main.py won't show up because it's a set. You can't have duplicate values. So that's what we are trying to do. With this, we have all of the file paths that are present in both of the indexes merged together in one single set. Now what we are trying to do is compare. So we want to compare the hash of the first index with the hash of the second index. So we'll just do index hash is equal to index.get file path. Okay. So if you remember again, the index is again something like this, main.py and a hash, right? So the index hash is going to be this value. Then we'd also get the index value of the last commit. So we have last index hash is equal to last index files dot get, and I'll pass in the same file path. Now see, I've done dot get on purpose. I've not done something like index at file path, correct? I've not done this because if I do this, it means that I know that file path is present within the index dictionary. And at this point, I'm not sure if the file path is present in index or not. That's because one file might be present in the last index files, but not present in index. That's why we are doing index.get file path. And we do it for both of them because it might also be the case that certain files are present within index, but they're not present within last index files. Okay. Now after this, I'll just check if index hash is present and let's say the last indexed hash is not present. That means this is not null and this is null. If that is the case, that means it is a file that has to be staged, because think about it logically. It's present in our current index. So coming back to our example, let's say I did init, I added main.py file, and then I committed. With these three operations done, we have one commit object and our index is empty. After that, let's say instead of adding main.py again, I add hi.py, a newly created Python file. So in this case, I do hi.py, the status is called after that. So now the index is the hi.py file. The last index contains this main.py file. So if I do index hash is equal to index.get file path of this hi.py, the index hash will be present, but the last index hash won't be present because in our last commit, which is this thing, these three operations, we did not do hi.py. So it doesn't know about the existence of any hi.py, because remember, what we have over here is a snapshot of the last thing that we had committed, and we had only committed main.py. And that's why if index hash and not last index hash, that means it exists in the current index. So hi.py exists in the current thing, but it does not exist in the last commit. That is a good sign for us that yeah, it's a staged file. So what I'm going to do is remove this and just have staged files is equal to an empty list. Then for every file path that is present here and follows this logic, we can just do stagefiles.append and let's pass in a tuple. Here we know that it's a new file that has been created, so we can just attach that metadata or some information about that commit, because I just proved it to you. If it's not present in the last commit, which is hi.py, it's a newly created file. Let's say instead we had main.py here. Main.py exists in the new index. It also exists in the previous commit or the previous index. So in that case, maybe the file has been modified, but we can't be totally sure that the file has been modified or not. We'll have to compare their hashes to know if the file has actually changed, because it can be the case that I do these three operations, I don't make any changes to main.py, I add main.py again. So the hash of both of these things are going to remain the same, because as we have proved before, if we given the same input, the output or the output hash is going to be the same with SHA1. And that's what we're going to make use of. So our next condition is going to be that, let's say the index hash is present and the last commit hash is also present, or the last index hash is also present. And we also have to check that the index hash is not equal to the last index hash. Because if it's not equal, that means the file has been modified. And if the file has been modified, we will add it to the staged files. So here I can just attach modified and then pass in the file path. So that is it for the staged files part of thing. Let's go ahead and print it out. Here I can print out the stage file like this, or what I can do is here check first if staged files is there. This line will check that the stage files is not null and it is not empty. If it is not empty and not null, well, it can never be null. We are initializing it with an empty list. So if it is not empty, in that case, we want to go ahead and print the changes that are to be committed, or as we know it, the staged files. So here I'll just do changes to be committed. After that, I'll go over this entire staged files thing. So I'll have for file path in sorted staged files. And we're not just getting the file path, we are also getting the status, or whatever you want to call it. So I'll just call this stage status. If it's a new file, it's modified. So for that, we'll just go ahead and print after leaving some space. So I'll just leave like 3 spaces, I guess. And then I'll pass in the stage status followed by the file path. That looks good. Now what I like to do is, well, just create another terminal because I want this example to stay so that we can talk further for our other things in status. And now I just want to do Python 3 main.py status. And as you can see, we are on branch master, but nothing else shows up because we have not staged anything. So let me go ahead and add the current directory. Then again, I'm going to do status. And here you'll see on branch master, changes to be committed, modified is .dstore, modified is main.py. That's correct. We have modified main.py and the system file, maybe the system automatically changed it. Also, now what I'd like to do is hello there. So let's see if hi.txt shows up or not. So again, I'll add all of the files. I'll do status and it says changes to be committed, modified test hi.txt. That's great. Cool. So our staged files part is now working. Now the next thing is unstaged files. Unstaged files is this thing, what files have been modified, but they've not been staged. For example, if I go ahead and update this hey.txt, that is a file that has been modified, but has not been staged yet. So those are unstaged files. For unstaged files, think about it logically. How will you figure out if the file has been modified, but it has not been staged? For that, you'll have to check what files actually exist on the disk right now relative to our working directory. So all of the files that are present in our current Git repository. So all of the files here. Then for each of the files, we need to calculate the hash to check if there's any changes. Because if we calculate the hash and if the hash matches the hash of this index, so all of the files that have been staged, if it matches with their hash, it means we have staged it. But if it does not match, that means we have unstaged files, correct? So we need to figure out what are, first of all, the working files within this directory. So here itself, just below this thing, I'm going to figure out all the files present within the working directory. And again, this is going to be a mapping between the file hash and the file name, or I should say reverse, because it's a mapping between the file name and the hash. That's what we are trying to do. So we are going to have working files, which is equal to a dictionary like this. Then we'll go over all of the files that are present in the directory. Now, how do we get all of the files in the current working directory? So for that, we are going to go ahead and create a function called get all files. After that, we are going to get a list of files, which is an empty list initially. Then we're going to go over all of the files that are present in this particular directory. Now we know the path of this current directory. If we just do for, let's say, item or path, whatever you want to call it, self.path.rglob. We have done this before, right? We recursively yield all the existing files within the directory. If you go around and search for rglob, you'll notice we have done this before. Recursively traverse the entire directory. If you want, you can go ahead and create this as a reusable function. But in my case, I'm fine. One thing that I do want to do is ignore the .git folder. So I'll just do if.git in the item.parts. I want to continue. I won't go any further. In your case, it would probably be .pygit because you might have changed it to .pygit. But in my case, it's just .git. Then I also want to check if the item is a file, because if it's a file, only then do I want to add it to this files list. And if this item is a file, in that case, I will do files.append, add the item, and then I'll just return this files at the end. Simple logic, nothing too complex. Let's copy this and, well, iterate through this now. So what I'll do for this is just go over this entire directory or the entire list that we've found out. And it is self.get all files, gives us a list, and then we'll find out the relative path. So what is the path of this thing relative to the entire global directory? So we have relative path is equal to item.relative to self.path. So that gives us a relative path, but also we have to stringify it. We want to convert it into a string no matter what. And then we will read this particular item. So let's go ahead and have try content, and actually let me just put except first. Except if it errors out, we're just going to continue because I don't want to move any further. I mean, I don't want to throw any error message as such. It should not stop the execution of our entire program. And now we can just do content is equal to item.read bytes. Cool, because we know get all files is going to give us a list of all of the paths, right? If we go back to get all files, what we are appending to this is a path. So what we are going to get as a return type is going to be a list of path, not list of string. Remember that it's a list of path. And that's why when we do item.relative to self.path, it will give us a path, but we need to convert it into a string because we want a relative path out of it. Why is a relative path needed? Because we want to put it as the key of this working files. After this, we are going to create a blob, which is going to be blob passing in the content. And then we can just do working files add blob is equal to blob.hash. Correct? And this hash is a function. So yeah. So with this, what we have done is created a mapping of file names, which is the relative file name. So it could be main.py or branch2.txt or test/test2/hello.txt followed by the hash. And the hash is created by just doing blob.hash. Nothing too complex. We're manually creating the hashes here. And we create the hash by wrapping it in the blob object. So we read all of the files that are present here, create its hash, and then the mapping is created. And actually we don't want to do blob here, sorry, we need to do relative path. As I said, we need to create a mapping between file name and hash. That's what I'm doing here. Okay, now that we have all of the working files, we can go ahead and figure out what are the files that have been modified but not staged. And for that, first of all, I'll just go ahead and create a variable called unstaged files, which is equal to an empty list. And then I'll do unstaged files. Well, not unstaged files directly. What I have to do is loop over all of the working files and then check if that working file even exists within the index. If that exists in the index, then I want to check if their hashes are equal. If they are equal, well, they're not unstaged, but if they're not equal, they're unstaged. So let's go ahead and quickly do it for file path in working files. then if the file path is present in the index, and that means if we come back to our example and we do these three operations, init, add, and commit, and after that we do status, what it's going to do is go over all of the files that are present within this directory. It checks that, hey, yeah, test/hi.txt or test/hey.txt is not present in the index. If it's not present in the index, they're not unstaged, because unstaged only means that the files have been modified, but they have not been staged. Git is not keeping track of these files in the first place, so they don't matter to us. What matters to us is, let's say we add the main.py, but then we again modify the main.py, right? So we again do add main.py, but after modifying the main.py. So this is unstaged files. To put it very simply in a statement, this is the case where you stage a file, then modify it, but then you don't stage it again. That's unstaged, all right? And that is the case we are trying to handle. Now, if that file path does exist in the index, that means we had staged this file before. Now we'll just check if working files at file path is not equal to the index at file path. If both of their hashes are not the same, in that particular case, we need to do unstaged files dot append, and then we'll add it to the file path. That is the unstaged files. Now what we want to do is go ahead and print it out. So we have these things. We'll print it out here. If unstaged files is present, then what we want to do is loop over this unstaged file. We don't really get the status here because they're all modified. We get the file path. So we just display the file path here, and the status can be modified because, as I said, all of the files are modified. Then we can also say changes not staged for commit. Also here, let's fix the spelling error, and yeah, we're good. So this looks good. I want to save this file and I want to just go ahead and do status again. So we get changes to be committed and changes that are not staged for commit. Because remember, when we have this changes to be committed, all of these show up because we did add all of them. So we had done python 3 main.py add, which added these three files, as you can see over here. This shows up because I saved the file, So since I saved this file and I edited this file, main.py shows up. I also modified the hey.txt, if you remember, just to showcase it to you. And just to showcase back to you, let's say I remove these triple A's. I come back, then I do status again, and all I have is the main.py, because when we call status, it is automatically checking at this very time that, hey, listen, what is the hash of this hey.txt? What is the hash of this hi.txt? And if this hash matches the hash that is present within the index. That's why we have that issue. So let's say I do python main.py add. So I add all of the files now. After this, I do status, and this line does not show up anymore because I had edited the main.py. Now it's no longer edited because I've added it to the index or to the staging area. So it's not unstaged anymore. So we have verified that this also works. Cool. Now the next thing is to figure out what are the files that are untracked. And this should be quite easy actually. Why? Because we have the working files with us. But first, let me just explain to you what untracked means. Untracked means that they are completely new files that Git doesn't know about. So they are all of the files that Git hasn't started tracking yet. And how can we know Git hasn't started tracking yet? We'll just look at the previous commit, and if the file is missing from the previous commit, that means we're not tracking it anymore. And remember one thing, by the way, the file should be completely missing from the last commit, and it should also be missing from the index, because if it's present in the index but has not been committed, that means it's unstaged. It doesn't mean that it's untracked. Okay? So here we'll just go over all of the paths that are present within our working directory. So we have for file path in working files. Then what I'll do is check if this file path is present within the index, correct? If it's present within the index, I don't want to do anything because I care about it not being present in the index. Because if it's not present in the index, it's untracked. And then I'll also check if this file path is not present within the last commit. So I'll just check if this file path is not present within the last index files. Remember, last index files is a mapping between the file names and the hash values. So when we do file path not in last index files, we are checking the keys. So we are checking the file paths essentially. And if it's not present within index in the last commit, then what we do is say that this is untracked. So I'll just create another variable called untracked files, which is equal to an empty list. Then I'll have untracked files dot append, and then I'll add the file path. Now let's go ahead and display it. So similar to unstaged files, I'm just going to print it out here. If untracked files is present, then what I want to say is untracked files. Then I'll go over all of the files that are present here within untracked files. And then I'll just list out, well, all of the untracked files, correct? So there we go. Now I'll go ahead and do status again. It just says these three things or these two things. So what I'll do is create a totally new file. Let's call this hello.txt, hello world. Now I'll again do status. And now we have untracked files. Because Git doesn't know about it, it's totally untracked. Also notice that changes not staged for commit modified main.py again shows up. That's because we just edited main.py and we've not added. So yeah, that's a very good confirmation that everything works. Now finally what I want to do is what files have been deleted. Now how can I know that a file was deleted or not? The way we are going to do it is that we are going to detect a file that was staged is now missing from the working directory. How is this different from not staged, you might ask? How is it different from unstaged? It is different from unstaged because if the file was present within the index, but it's no longer present within the working directory, it means that the file has been physically removed by a person. So it's deleted, it's no longer present. That's what we are doing. Unstaged doesn't check for that. Unstaged compares the working directory against the staging area. And if the working directory differs based on this condition that we have, it's unstaged. But in our case, we're kind of doing the opposite here. Here it's going through every working file and then checking if it's present within the index and if their hashes is not equal. What we are trying to do is go over every file within the index. And then we are checking if the file is not present within the working directory. So kind of the reverse of this. So what I have to do for this is for file path in index. So I go over every file in the index and then I check if the file path is not in the working directory. That means the file has been removed. Earlier, again, I'll just revisit this because it's a subtle difference. Here we were just checking that all of the files that are present here, if they're present within the index and their hashes don't match. If the hashes don't match, they're unstaged. But in this case, we are going over all of the files that are present in index. So let's say I had done all these three commands. Then I modified main.py, let's say. I added main.py again. So it's present within the index. It's in the staging area. But now what I do is delete the main.py file completely. This will show up in the deleted files because we are going through all of the files in index. This still exists in index, the main.py, but it's not in the working directory anymore. And now I'll just create a variable at the top, deleted files, which is equal to an empty list. Now I'll scroll down again and I have deleted files.append and I'll append the file path. Then similar to this logic, let me just go ahead and have if deleted files is present, then we are just going to do for file path in deleted files. Also, this is going to be deleted files. This is going to be for \n. And then I can just do for file path in sorted deleted files. We just say deleted. and the indentation is the same as this modified one. Okay, now let's say I go ahead and do python3 main.py status, nothing shows up, but now let's say I do python3 main.py add everything. So everything is there. Now the status is just everything that should be committed. But now I'll just go ahead and delete, let's say, hello.txt. Now I'll do status again. And now it shows up the deleted file. And if I restore it again, do status again, that thing goes away. So everything works as expected. Now let's say I just do add again, and then I just do status. So these are all of the changes that will be committed. And now I'll just do the commit. So commit -m everything. To show it to you that everything works, I'm just going to do log. So it logs out everything we've committed to date in this specific branch, obviously. And then I'll do status. On branch master shows up nothing else. And that's because none of these conditions are fulfilled. Everything is up to date. So now, let's say the user does do status after this. What we want to display is that, hey, you have nothing to commit. Your working tree is clean. So here I can just put in a condition that, hey, if not staged files and not unstaged files and not deleted files and not untracked files, if everything is empty, all of the conditions are empty, in that case, we'll print out nothing to commit, working tree clean. And that's great. Now again, we'll have to do add because main.py has changed. So we'll do add. Now we'll do status. Only main.py needs to be committed. So let's do commit -m main.py. I'll do status now, and it says nothing to commit. Working tree is clean. And with this, we have figured out the entire Git status. Now, if you want, there are various other options that you can implement, and that would be great. But with this, I've completed the Git clone from my side. With just 772 lines of code, we have completed a very simple Git clone, but it's something that can be extended very easily if you think about it. So I would recommend you to go ahead and try out how to implement cherry pick, how you can cherry pick a specific commit or whatever. Then checking out a commit. That's also a good option to implement. Stash would also be a great one to implement. Merge would also be a great one. If you don't already know what cherry pick and stash are, you can learn about it and implement it on your own. The tag would be a really good one to implement because you don't even know where tags live, right? They are a special refs place where they live. So in .git folder, in refs, you have heads, right? You have another folder here called tags where you can store your tags. So if you want to implement this, you'll have to do your own research, and that would be a really good thing to implement in your Git clone. And that would give you a lot of confidence as well. So these are like the basic 5 operations. If you can do it and send it to me, I would love to take a look at it. Or if you want me to cover it in another tutorial, let me know. I would be happy to do so. But yeah, this is it for this tutorial. Thanks for watching, and I'll see you in the next video.